Hello everyone, I am Varun Joshi and welcome to Cloud with Varjosh. In this masterclass, we are diving into storage in Kubernetes, covering everything from Docker volumes to Kubernetes persistent volumes, storage classes, config maps, and secrets, all in one place. Whether you are preparing for the CK exam or just looking to truly understand how storage works in containerized environments, this session will give you both solid conceptual foundations and real world demos. If you are on the CK journey, be sure to check out the full CK playlist available right here on the channel. It is designed to guide you every step of the way. What I have done is I have combined everything from day 24 to day 28 of the CKA 2025 series into one single video. So you can learn Kubernetes storage end to end, especially if you prefer mastering a topic in one focused session. Timestamps and all relevant links are in the description below. Let's get started. What you see on screen is a Docker host. That Docker host is running 3 containers. Here is an image, and this image was created using this Docker file. The Docker file you see here is the same that we used in day 3 of our course. If you have any questions pertaining to this Docker file, I would request you to go and watch day 3's lecture. The image that has been created using this Docker file is of 50 megabytes. 50 megabytes is used for simplicity. The image that this Docker file will create will be of more size. We know that a Docker file can consist of multiple instructions, and these instructions can be bifurcated into 2 categories. First one is instructions that create layers, and another instructions that do not create layers. The instructions that create layers are from, run, copy, and add, and non-layer creating instructions can be seen here. But what are layers and why are we calling these layer creating instructions? So what happens is any instruction that generate data or modify the file system in any way are called layer creating instructions. If you look at from, then from uses a base image, and that base image uses some sort of storage. Hence, from is a layer creating instruction. If I look at workdir just specifies which one will be the working directory in the container. Hence, this does not take any storage. This helps the image in some way, but is not directly impacting the file system. So non-layer creating instructions are like metadata to the image. They do not perform a storage intensive task, any task that will generate data, but what they do is they help your containers either in build time or at runtime. Then you see add. Since add is used to copy data from your, let's say, Docker host to your image, hence add also generates data. Run, you use it to install packages in your image, hence run also generates data. Then expose and cmd are non-layer creating instructions. Now what I also understand from this image is more task my layer creating instructions will do, the larger the size of my image will be. If I am installing multiple packages in the run instruction, then accordingly my image size will be larger. If I am copying data from my Docker host to my image which is of large size, then also my image will be of large size. Hence, it is recommended that you distribute these commands into separate sections. For example, there could be a stage where you are doing the build, and there could be a stage where you are defining your runtime instructions. So what you are essentially doing is you are using multiple stages in your Docker file, and few tasks that are only necessary for building your software are performed in a build stage, and then the things that are required to run your application, which are a mandate for your application, are available in the runtime stage of your Docker file. And I'm just using 2 stages as an example here, but you can have multiple stages. And if you have such kind of approach, what happens in the end is your image size is reduced, which is what we all want. The mechanism that I am discussing right now is called Docker multi-stage builds. If you have any confusions pertaining to this concept, then you can look at day 5 and understand this. But Varun, this is fine, but why are we discussing layers? So when you create an image consists of read-only layers. And why I am calling this a read-only layer? Because if you see, if this image is here, this image is shared between all these 3 containers, and any of these containers cannot modify this image. Hence, we are calling these layers as read-only layers. So what I mean by this is, if I talk about the total storage consumed by this Docker host at this moment, then we will only say that only 50 MB is consumed by Docker, because these 3 containers that are running are not using any additional data. They are just sharing this image, and since the image is read-only, they cannot modify this image directly, but they can write new data. And when these containers write new data, we call that a writable layer. So for example, if this container 1 modifies a certain section of this image, then it will either modify some data or generate new data. And those changes, that delta, is the writable layer. So when you run a container, you get a read-only layer, and that read-only layer is the image. And then whatever you write on top of it becomes the write layer. Whatever modifications you do, they become the write layer. If I scroll down, you see that now these 3 containers have started generating some data. If you see, this container has generated 4 megabytes of data, this one 10, and this one 6. This is understandable. So I also want to show you these layers in the terminal. So I am in day 3's directory, although we are sitting at day 24, because I want to demonstrate creating an image, and then we'll see the layers in that image. So here is my Docker file, and this is the same Docker file that you saw in the screen a few moments ago in this diagram. Now let's do one thing. I'll write docker build -t. I will name this my image, and then I'll add a dot, which signifies that the context is the current working directory. I'll press enter, and it has started building my image. Now once my image is built, I'll run docker image ls, and I can see that my image exists here, and then I will run docker history my image. If I press enter, you can see that anything that consumes storage is part of the layer creating instructions. Hence, whatever we discuss, the read-only layers are the only ones that modify the file system in any way. Let's go back to our diagrams now. And here this container has consumed 10 megabytes of space. What happens if this container dies? This 10 megabytes of data is lost, because we do not have a persistent storage with container 2, and containers are ephemeral. They come and go. Let's say if this container was just supposed to generate some data and then go, then how can we ensure that whatever data this container generated is saved somewhere? And here we have the concept of Docker volumes. The Docker volumes are there to ensure that data that you want persisted can persist. Let's move to the next section now. Docker storage. Docker handles storage via storage drivers and volume drivers. So whatever writable layers that we have been creating up until now, be it in Docker or be it in Kubernetes, what are we using? We are using the storage driver, as storage drivers handle the container's internal ephemeral data tied to the container's life cycle. So as soon as this container dies, this 4 MB of data is lost. And why is it lost? And who is playing a role in helping create these writable layers on top of these read-only layers? It is the storage driver that is helping us. Now think of them as file system for containers, manage container, internal storage, and file organization. Kubernetes follows the same. So Kubernetes has something called Container Runtime Interface, CNI, that interacts with the storage driver. The examples of storage drivers are overlay FS. This is the most widely used and is also the default on Linux systems. Then there is ZFS. This one is an advanced one. Then you have AUFS. This is now legacy. The advanced version of AUFS is overlay, which is now being used. Then you have ButterFS. This is for large scale environments. If I want to verify which storage driver I am using, I can go to the terminal and I can simply run docker info. This will dump me all the information about my Docker deployment. If I move above, I see here storage driver and we are using overlay 2. And if I go back to my diagram here, we have volume drivers. So when do volume drivers come into picture? Whenever you attach external storage to your containers, volume drivers are active. They handle external persistent data that exists independently of the container's lifecycle. So even if this container dies, my data stays here. So for example, if you have a laptop and you have connected an external HDD to your laptop, and if your laptop crashes, God forbid, I hope that never happens, but your data is still safe in your hard disk. Similarly, if this container dies, any volumes that I have mapped to this container externally will stay. That data inside that volume will remain. Think of them as external hard drives for containers. Manage persistent data storage that exists outside containers. Now, when I talk about Kubernetes, here we have volume drivers. Kubernetes has something called CSI plugins, container storage interface plugins. They help Kubernetes to map volumes from different cloud providers or from different sources. So we'll discuss the Kubernetes CSI plugins in the next lecture. For now, the examples of volume drivers that are used by Docker are: first is local. This is the default driver, and in the demo we'll see the local driver is being used. And different cloud providers like AWS, Azure, GCP, they will have their own drivers which can be used to mount storage from their cloud onto our Docker containers. I hope this makes sense. Now, if you are thinking, if volume drivers exist, I don't need storage drivers, but that is not the case, because your containers will still use ephemeral data, will still have data that you do not want to persist. Hence, both of these work in conjunction when you are dealing with a production grade Docker deployment. Let's move down now. Docker installation. So first, let's look at this. Docker installation options. First is Docker Engine, second is Docker Desktop. Docker Engine is only available for Linux. Why is this? If you look at it architecturally, Docker Engine is only designed for systems that have Linux kernel. Does macOS have a Linux kernel? Does Windows have a Linux kernel? They don't. Hence, Docker Engine cannot be directly installed onto macOS or Windows, but it can be directly installed onto any Linux distribution. That's because they all have Linux kernel as the base. Hence, Docker Engine runs natively onto them. But why does Docker Engine have this dependency on the Linux kernel? Because Docker Engine relies on certain features that Linux kernel has to offer, and these features are control groups, network namespaces, and many more. Second installation option is Docker Desktop. This is what we have been using. If you look at the top here, I have a Docker Desktop. If I go to the dashboard of that, you will see all the containers that are running. You can also see images, volumes that exist in my Docker Desktop installation. Let's get back here. When I install Docker Desktop encompasses a few things. It has a Docker engine. Yes, it does have a Docker engine. That's why we are able to run containers. Then it also has a Docker Compose. It has a GUI dashboard, which we just saw. But Varun, how is Docker Desktop able to achieve that? It is able to achieve that because whenever you install Docker Desktop onto Mac OS or Windows, there is a lightweight Linux virtual machine created, and onto that virtual machine, the Docker engine is installed. So all of you who have installed Docker Desktop, there is a small VM created, and if you're using Mac OS, then the Docker Desktop is able to create that VM because we have Apple Virtualization Framework and Windows has WSL2, which is Windows Subsystem for Linux. I hope this clarifies things. And Docker engine, again, it consists of, we saw that in day one, Docker engine consists of the Docker CLI, REST API, and the Docker daemon. Hence, Docker engine is of paramount importance. Now this is clear. Let's move to the next section. Next section is the demo. So let's go here. I'll clear my screen. I will run a command docker volume create my vol. As simple as this. I'm creating a volume. I'll press enter. My volume is created. Now I will run docker volume inspect my vol. I'll press enter and you see a volume is created, and this volume uses the local driver. This is exactly what we saw in the diagram. This one local is the default driver. Let's go here now. I will now map this volume onto a container. So let's write docker run -d. Name of the container will be my container one. -d is added so that this container runs in the background. Then I'll write -v as in -volume. Then I will say that whatever volume I have just created, my vol, just map that volume onto the app directory of my container. And you know, if I go back here, app is my working directory. This is where all the action is happening. This is where we have copied our app.py, and app.py is the logic of my application. If you want to deeply understand that, you can go watch day 3, but at this time you do not have to understand what this image will be doing for us. A running instance of this image will be doing for us. Hence, let's just concentrate on volumes for now. I go here and then I will tell this which image to use, and it will use the image that we just created, my -image. I will press enter, but before I do that, you see that the format is -v. First you mention the volume that exists on this host, on this Docker host on my Mac machine. But is it my Mac machine? We'll answer that question in a little while. And then we are saying that this is where you want to map this onto a container. And this format is similar. Docker uses this format for ports as well, for port forwarding. So if I go here and go to day 3, you see we use this command docker run -d. -p was for port forwarding. So we were saying here anything that comes onto port 8080 of the host should be forwarded to container port 80. First the host port and then the container port. And here as well, we are first writing the name of the volume that exists in the host, and then we are saying /app, which is on the container. Let's press enter now. It says that the container has been created. Now let's exec into the container. I'll use docker exec -it my container 1, and what I want to use is the born again shell bash. I'll press enter, and you see that I'm directly taken to /app directory. And why is that? Because this becomes the working directory for my container. So whoever copies something or whoever logs in into this container, by default they will be taken to this directory. So let's run ls here, and we, as expected, we see app.py here. What I'll do is I'll create another file, and I will write in this file, this is my delta data, delta as in the writable layer that I'm creating. And then I will write here, redirect this data into file.txt. I'll press enter, I'll hit ls, I see that file exists, I'll cat on this file, and I see this is my delta data. Now I will exit out of this container. What I will now do is I will delete this container, docker rm, I'll add a hyphen flag because that container is running and I'm deleting a running container, which is why I'll have to force delete it. I'll write my container 1, I'll press enter now. It says my container 1 deleted. The container is gone. Now what happens by default is whatever you see here, my -vol, this volume gets created in a folder called var lib docker, and inside that there is a volumes directory, and inside that these volumes get stored. They take the storage of your host. So let's do one thing, let's cd into this. No such file or directory. Why is it? If I were on a Linux machine, then this would have worked, but I am in a Mac machine, and as I said, we have installed Docker desktop, and behind the scenes Docker engine is configured onto a small Linux VM, but I am trying to access this file from my Mac machine directly. That will not work. So what I'll have to do is I'll have to log into my small Linux VM that Docker desktop created in my macOS and then access this path. Or I can create another container, map the same volume on that container and check if my data exists or not. So let's go with the second option. I will run docker run -it -rm states that remove this container once the command is done, and our command will be accessing the shell. And -it is for integrated terminal, and then I will write -v. The volume name that I want to mount is my vol, and where I want to mount it in this container, I want to mount it onto /app. I'm not naming this container here, and I'm asking this container to use the alpine image, and then sh for shell. I'll press enter and I'm inside the container. If I run ls, I see that the first directory is my app directory. If I cd into the app directory and hit ls, file.txt exists here as well. This is because this is a volume that we created. Now any container who has this volume can store the persistent data onto this volume, and even then if that container goes away, our data will stay safe. If I cat into this file, you can see that this is my delta data. This is what we echoed into this file. Now I can exit this container and the container is gone. If I run docker ps, I do not have any running containers that we just created. These three are part of my Kubernetes in Docker, that is kind installation. These are running my Kubernetes workloads. One is the control plane and two of them are acting as my worker nodes. Okay, so what I will do is I'll clear my screen now and let me think if I have anything else to tell you. Yes, let's discuss. I'll go to my GitHub notes, and please visit these notes, and I would be very thankful if you can star this repository as well. Now I'll click on types of Docker volumes. What we have discussed, the volume that we created and then mounted, these are called named volumes. One thing I want to add here is we first created the volume and then mapped the volume. We first used docker volume create, and then once the volume was created, we mapped it. However, we could have directly run this command, and this command behind the scenes would have created the volume for us. Okay, so named volume is something that we just use. This is the default Docker managed volume, and if you are using Docker volumes in production, then you would be using the named volume. Second one is bind mount. This one mounts a specific host directory to the container. Now, if you are mapping a host directory, then your container should have appropriate permissions onto that directory. Then only writes or reads or executions will happen, because if you see cons is tied to the host path, can cause permission issues. Then there is tempfs. Tempfs is the volume that is mapped from your memory itself, from your RAM. So hence the performance will be very fast. However, if your container reboots, your data is gone. If your host reboot, then obviously your container will be down and also the data will be lost. So use this with caution. Majorly you will be using named volumes. Now, before I talk about this slide, I would want to visit day 8 again. We learned that Kubernetes was originally created by Google, and in 2014 Google released Kubernetes as an open source project. In 2015 itself, it came under CNCF, and CNCF in itself was founded by Google. However, now CNCF is independent body that works under the Linux Foundation. There are multiple key projects that are hosted by CNCF. Being a DevOps engineer, you would be working on these tools: Kubernetes, Prometheus, Istio, Envoy, etcd. etcd is the DB that we use in the control plane of our Kubernetes deployment. And then we have Helm. Helm we'll also see later in this course. Core DNS is the DNS that we have been using in Kubernetes, and there are many more projects. So let's come back to today, that is day 25. This line says that Kubernetes follows a highly modular design. Instead of embedding all functionalities into the core, it relies on plugins, add-ons, and third-party integrations to extend its capabilities. Let's break this definition. Firstly, since the inception of this course, we are talking about decoupling. If you remember, we started with a monolithic application. We decoupled that into 3 different categories: the front end, the back end, and the database. Then we further evolved that design into a microservices architecture. And in microservices architecture, we divided the application into different microservices, and these microservices are independent of each other. For example, if my wishlist microservice is down, then my orders and payments and rest of the microservices pertaining to that application will continue to work fine. And by decoupling these things, we ensured that not the entire application is down at once. That was our use case for using microservices. Each microservice served a specific purpose. For example, if you have the wishlist microservice, then wishlist microservice just held the logic of how the wish listing would work. How can people add products in the wish list, how they can remove, and so on. So the application code per se was only concerned about wish list, nothing else. Similarly, if you come to the text that you see on screen, Kubernetes has a core purpose. And what is the core purpose of Kubernetes? The core purpose is container orchestration. Kubernetes does not care how a container or a pod is created. Kubernetes does not care about the underlying networking. Then what is the core purpose? The core purpose is container orchestration. And that is the reason, so Kubernetes has said, my core is ensuring the container orchestration works. Rest anything else, I have outsourced to different companies, to different vendors. However, what Kubernetes has done is it has created some standards. So for anything that I have outsourced, there are certain standards that you must adhere to. And as long as you adhere to those standards, you are good to use your own system. My core will remain same, but anything else can be added. So let's zoom in into this concept and understand what is part of Kubernetes core and what is not part of the Kubernetes core. The core is your control plane components and your node components. The control plane component is your API server, which acts as an entry point for intra or inter-cluster communication. There are many more utilities of API server, but we are just mentioning the critical ones in this lecture. If you want a deep dive into control plane, data plane, then I would recommend you go to day 7. That is where we have discussed the Kubernetes architecture in greater detail. We have also demonstrated how each component behaves when you create a deployment. So it's a good place to start. Then you have scheduler. Scheduler is responsible for scheduling workloads onto nodes. There is controller manager, which ensures the desired state of the cluster matches the current state of the cluster. etcd is the database. Then there is cloud controller manager, which ensures that your Kubernetes deployment can interact with the cloud provider's resources. For example, if you are on AWS, you can seamlessly communicate with secrets manager, KMS, application load balancers, and many more things. Then you have node components. In node you have kubelet. Kubelet is responsible to ask the container runtime to create the container, monitor the containers, and there are a lot more functionalities that kubelet performs. Then there is kubeproxy, which performs service to pod networking. So these things are Kubernetes core. So the developers, the Kubernetes community. What is the Kubernetes community? Kubernetes community is a group of passionate developers, DevOps engineers like you and me who are eager about technology. And not just people, the Kubernetes community also comprises of organizations like Google, AWS, Red Hat, Ericsson. They all have some contribution in the Kubernetes development. So these organizations and these people form the Kubernetes community. So the Kubernetes community is responsible to handle the Kubernetes core. If, let's say, deployment introduces a new feature, I'm talking about the Kubernetes deployment object. If there is a new feature introduced, it is the Kubernetes community that is responsible for that. They are making the development, they are testing those things. If there is an update in the controller manager, it is Kubernetes core who is working on that. So anything pertaining to these things is the responsibility of Kubernetes community and hence falls under Kubernetes core. Now, what is not part of Kubernetes core? First categorization is plugins. What is a CNI plugin? CNI plugin is associated with networking. Kubernetes core says, I don't care how one pod talks to another pod. That's not my core task. My core task is container orchestration to establish communication between pods irrespective of which node they are residing in. Use a CNI. Then there is CSI for storage. CRI is for container runtime. Then there are various add-ons like ingress controllers. So ingress controllers we'll see later in this course. They are responsible for distributing traffic in your Kubernetes cluster. They support something called host-based and path-based routing rules. We'll see them in detail later in this course. Then there are different monitoring tools. Monitoring tools could be tools like Neuralink, Prometheus, and there are many more third-party tools. Service meshes. Service meshes define how the microservices within your cluster will interact with each other. What will be the security of those things? So there are service meshes that you can use as add-ons. Then there are third-party extensions. As you progress in your Kubernetes learning, you will learn about all these things slowly and steadily. So don't hurry as of now. Just take these things as a high-level understanding, and as and when we progress with this course, there are a few things that you see on this screen we'll be zooming into. There is Helm, and there is Prometheus, and there are many more things. So these things are not part of the Kubernetes core. In this particular lecture, we will be zooming into these plugins and how they play a role in ensuring your workloads run seamlessly. Let me scroll down. This is the Kubernetes core, like we just discussed, and then these are plugins that extend the capabilities of your cluster, and how they extend these we'll see in detail. The first thing I want to discuss is CRI. CRI is Container Runtime Interface. If someone just says CRI, then CRI is essentially a set of standard or a set of rules that are defined by the Kubernetes community, and Kubernetes community works under the governing body CNCF. Hence, any company or any person or anything that adheres to the rules set under CRI can write their own container runtime. CRI essentially is an interface that defines a set of rules, a set of standards. The expanded form for CRI is Container Runtime Interface. Then there are different plugins for CRI. Plugins are something that are developed by developers and hence companies. The examples are CRIO, Containerd, Podman, Kata containers. The responsibilities of a CRI plugin, of a container runtime plugin, are container lifecycle management, image management, logging, and security. These are not the only responsibilities. There are many more. These are just an example of the responsibilities that a CRI plugin performs. But Varun, help me understand one thing. Why didn't Kubernetes core include CRI in part of the core itself? Why is it separate? Because container runtime is just pulling the image and performing all things container related. But like I mentioned before, Kubernetes core is container orchestration, not creating your containers and ensuring security for them. This is not the core of Kubernetes. Core is container orchestration. And again, anyone who adheres to this CRI can write their own container runtime. You also see Containerd here, and Containerd in itself is developed by the Kubernetes community and is a CNCF project. Then why can't Containerd be the default container runtime, and why go to extents of having so many different runtimes? That is because each project, every application has its own requirements. You cannot have all of them use a single runtime. So I'll give you an example. So Containerd you will see is the default for most setups, and it is lightweight and optimized. Then there is CRIO, which is also called Cryo. Cryo is designed for OpenShift and tightly integrates with Kubernetes. What is OpenShift? OpenShift is also a distribution of Kubernetes like Amazon EKS, Azure Kubernetes Service, and Google Kubernetes Engine. There is OpenShift, which is by Red Hat. OpenShift is also a distribution of Kubernetes, and OpenShift uses Cryo. So any deployment that you will see of OpenShift will be using Cryo. And then there is Kata containers. It offers hardware isolation for better security. So if your requirement is that, then you could use Kata containers as your CRI plugin, as your container runtime. Then there is gvisor. Gvisor is by Google, and it provides user space sandboxing for untrusted workloads. Now, do you have to know these things in detail? No, but I want you to have an overview of all these things. Then there is CNI. CNI is Container Network Interface. This thing sets a standard for the rules that anyone who is writing a CNI plugin must adhere to. Examples include Calico, AWS VPC CNI, Flannel, Cilium, The responsibilities of a container network interface plugins are pod networking, manage how pods can speak with each other, IP address management, routing and connectivity within your cluster, and security enforcement. How security enforcement? Later in this course, we'll look into network policies, which ensures only certain workloads can communicate with each other depending on your compliance and security needs. So why do we need a CNI plugin? Same question that we answered here. Why can't I have a standard CNI, only one CNI for everything? That comes down to requirement. If I talk about these cloud providers, the big three, Amazon, Google, and Microsoft, then they all have their network tooling. Now, not all network tooling is same. Hence, we need a different CNI plugin for each of the cloud provider. For example, AWS VPC CNI is used in Amazon EKS. Similarly, AKS will have Azure CNI plugin. But Varun, Kubernetes is open source, firstly. And secondly, EKS, AKS, or any cloud provider's managed service for Kubernetes is using vanilla Kubernetes. And then they are doing some extensions on top of that. So can't I use Calico or Cilium when I'm working with Amazon EKS? Is it a mandate to use AWS VPC CNI? No, you can use any CNI plugin that you want to use, even if you are on a cloud provider. But what happens is, when you are on Amazon and when you are running an EKS cluster, there are certain features provided by the VPC CNI plugin that are not available anywhere else. For example, pod security group, they are available with AWS VPC CNI, and as far as I remember, I don't think any other CNI plugin offers that. Hence, it is recommended that you use cloud native CNI plugin whenever you are on a cloud provider. Now, how it also helps is, when you are troubleshooting or when you are stuck somewhere, then you can use the native cloud providers support to solve your problems. Hence, that is a recommendation that you should go with the CNI plugin provided by the cloud provider itself. But why would you want to use something else? See, there are always corner cases. There are always specific use cases. Then why would you want to use Calico? Because Calico is ideal for environments that require advanced security and BGP routing. If your requirements are that, then you would be using Calico. And this is not only limited to cloud providers, even on-premises deployments could be using these CNI plugins. And of course, with on-premises, you cannot use AWS VPC CNI or Azure CNI until and unless you are ready to do some tuning and tweaking. You would be using other CNIs. Then there is Cilium. This is ideal for high performance networking and security deployments. There is Flannel. Flannel is quite lightweight, but Flannel does not support network policies. Then there is ViewNet. ViewNet is used for encrypted communication between pods. So when you want that type of a security, you can choose ViewNet. Hence, there are multiple options, so that you as a consumer can choose the CRI or CNI based on your requirement. So why did I fit this topic here is because of CSI. Since in the next lecture we'll be discussing Kubernetes volumes, I thought it will be best if I introduce CSI before going to the Kubernetes volumes. So what is CSI? So if you remember, in the previous lecture, we discussed Docker storage is handled by two drivers. First is the storage drivers, and then there are volume drivers. Storage drivers are responsible for ephemeral storage. So anything that goes with the container lifecycle. So if a container dies, that data also dies. If you have any confusion pertaining to this concept, I would recommend you watch day 24, because there we discussed these things at stretch. And Kubernetes follows the same. If you create a pod and then you write some data in the container that is part of that pod, and then you terminate that pod, then your data is essentially gone. because that data's writable layer, because that container's writable layer was ephemeral. So as soon as the pod died, the data went away with that. So the ephemeral data part is handled by storage drivers, and then there are volume drivers. So whenever you add a persistent disk to your pod, maybe because you want to retain some data, it could be your logs or your application data, or you are running stateful applications on your Kubernetes cluster, then you would be using volume drivers. Now volume drivers are there to persist data like we discussed. So whenever you will be adding an external disk to the container in Docker, you would be using volume drivers. Kubernetes follows something similar, but they have CSI to handle this. Why do we need container storage interface? You need container storage interface plugin to interact with the external storage. So CSI, like we discussed about CNI and CSI, this is container storage interface. These are the set of rules, set of standards written by Kubernetes community that a person must adhere to, and if those set rules and standards are adhered, that plugin can work with Kubernetes to assign external storage to your pods. Examples include AWS EBS CSI driver, Google's persistent disk CSI drivers. So there are many drivers that can help you connect with external storage. So for example, if you are on Amazon, you would need a CSI plugin which can help you interact with Elastic Block Store, which is the block storage in AWS. If you want to access their EFS, there are drivers for EFS. If you want to access persistent disk in GCP, then you would use GCPD CSI driver. Similarly, there are drivers for various storage vendors which you would be using to interact with that storage. For example, if you are running your cluster on ESXi hosts VMware, now Broadcom, then what you would be doing is there would be a driver that can help your pods connect with the VMFS in your ESXi. So these are the drivers that enable that communication with external storage. So responsibilities of a CSI driver: volume lifecycle management, snapshot and cloning, expansion and resizing, dynamic volume provisioning. So rest of these are self-explanatory, but dynamic volume provisioning is whenever I create a pod that says I want 10 GB of storage, then that 10 GB of EBS volume, if you are on AWS, is created and assigned to your pod. So I hope you have a good understanding of why Kubernetes follows a modular architecture, why there are plugins, why there are add-ons, why there are third-party toolings. Now, there are some benefits of this modular and extensible architecture. I want to quickly discuss those benefits, and before I do that, I would recommend you also go to the GitHub notes day 25, and if I go to references, you can find that I have added all the references. You can go to these places and this will have the official documentation. So this is the official documentation for CNI. If you are interested, I would recommend you go through these references and have further understanding of these plugins. I'll go back here, and I think it would be better if I teach the benefits right from here. Yeah, why Kubernetes uses a plugin based architecture. So the first one is interoperability. You can use various plugins, third-party tooling without disturbing the Kubernetes core, and this provides you better interoperability. Then there is flexibility and vendor neutrality. You know that there are various vendors for CNI, CRI, and also for CSI. You can choose which one works best for you. Encourages innovation. Now, since each company or each organization has its own plugin, third-party tooling, etc., then they can work on enhancing that specific thing. For example, if I talk about CRI, Kata containers offer something that Cryo does not offer. So it has an advantage where some customer is looking for highly secured container runtime. Then there is scalability and maintainability. Individual components can be scaled and upgraded independently, improving reliability and maintainability. So this is self-explanatory. I think that's all I wanted to cover. Before I start this lecture, I have a request. If you are liking my content, I would request you to like my videos, subscribe to my channel, and drop a comment. Even if it is just a hi or a thank you note, it will mean a lot to me. Let's get going with the lecture now. Ephemeral storage. Firstly, what is ephemeral storage? Anything that is temporary and goes away when the pod is terminated is ephemeral storage. So the first type I want to discuss today is emptyDir. Exists for the lifetime of the pod. So if you create a pod and create an emptyDir volume, that volume will be deleted as soon as the pod is deleted. But Varun, we have been using pods since the inception of this course, and we have been modifying the data, putting new data, and we are deleting the pod and the data was gone. Then what is special with emptyDir? Because we have been using ephemeral storage since the beginning. The difference is emptyDir enables data sharing between containers in a pod. So if I go to day 21, we discussed that pods can have multiple containers which mainly share networking and storage. Let's say I want to map a volume to my pod. I map a volume to my pod. Then I have an option to mount that volume onto a single container in a pod or to multiple containers inside the pod. So if I mount that volume to a single container, only that single container can access that volume. But if I mount that volume to all the containers, then essentially all the containers are sharing that volume. Previously, what was happening when you were creating a pod, you still had multiple containers, but the difference was, let's say if this is a Docker host in my example, let's say it is a Kubernetes host, and you created 3 containers, and all these 3 containers are part of a single pod. And let's assume all the containers were using the same image. What happens is the readable layer, we discussed what are read-only layers and writable layers in detail in day 24. I'm just giving a gist of it. So all these 3 containers that are part of the pod are sharing the same read-only layer. And then whatever new content they are writing, or if they are modifying any existing data, it creates a new writable layer. So in this example, the writable layer that these containers had created 4 MB, 10 MB and 6 MB of data. But here these writable layers were not shared between the containers. Each has its own writable layer. But what we are saying now is, assume that you have another volume now that's called emptyDir volume, and with that volume what you can do is, let me bring a volume here. Let's say this is the volume. Now if I share this volume with the pod, and then this volume is mounted onto all these 3 containers, then these containers are sharing any data that is written here. So any writable data can be shared between containers using this emptyDir volume. Previously, whatever ephemeral storage we have seen, in that scenario, all 3 containers that were part of a pod, for example, had their own writable layer. But with emptyDir volumes, each container will still have its own writable layer. That's understood. But if you want some data to be shared, you can map an emptyDir volume onto all these 3 containers, and then they can share this. Hence, we have written this point here in our today's lecture that enables data sharing between containers in a pod. I'm stressing on this point, all the containers in a pod. If there are 2 containers that are part of 2 different pods, then emptyDir volume cannot be used to share that data. But with the containers in a pod, you can use emptyDir volume to share that data. Third point is each pod replica gets its own unique emptyDir volume. So for example, if you create a deployment and that deployment has 5 replicas spread across, let's say 3 worker nodes, then each pod will have its unique emptyDir volume, and that volume cannot be shared between pods. However, the containers within a pod can share that volume as long as the volume is mounted onto all the containers. Then uses hosts storage. This behaves a little differently, so it depends on what sort of deployment you have. I am mentioning these things to maintain completeness so that these foundational concepts are engraved in your brain. So if I go to day 24, we discussed about Docker installation. We said that there is different type of installation that can be used in Linux, macOS and Windows. For example, Docker engine has a limitation, not a limitation, it is how Docker engine is architected. So you can install Docker engine only onto the OS that is based on Linux kernel. If I talk about any Linux distributions like Ubuntu, you can install Docker engine directly onto an Ubuntu VM. However, when it comes to Mac OS and Windows, what you do is you configure something called Docker Desktop. And when you configure Docker Desktop creates a lightweight Linux virtual machine, and then on that lightweight Linux virtual machine, Docker engine is installed. And once you have Docker engine installed, then you can run containers. But Varun, why are we mentioning this here? I am mentioning a point that uses host storage. So if you are on Ubuntu, then the underlying hosts storage is used. But if you are using Mac or Windows and you are using Docker engine, you have configured Docker Desktop, then the lightweight VM is your host storage. Having said that, even if you have a Linux lightweight VM, it is still using your base storage, but there is a nuanced difference which I want you to know. Your scenario, if you are using Mac OS or Windows, your host is Docker host is your lightweight Linux machine, because it is that lightweight VM onto which Docker engine is installed. So this distinction is important. Now let's again go to day 26. Uses host storage. That is fine. What are the use cases of emptyDir? First is scratch space. What is scratch space? Scratch space is temporary storage that is required for certain applications. Now, if you have an application that requires small amount of storage to begin with, not just small amount of storage, the highest amount of storage that can be available as scratch space is whatever your host can support. For example, if I have 100 GB of host storage that is directly associated with my host, then I would be supplying, let's say, 2 GB for scratch space as emptyDir volume. Then second use case is caching. Now, when I talk about host storage, take example of your laptop. Whatever storage your laptop has, that is your laptop's own storage. If I connect a USB drive onto my laptop, and that USB drive will be external storage for my laptop. Similarly, when I talk about big servers, you could have a server that has its own internal storage, and that internal storage can be thought of as like your laptop has its internal storage. So why are we discussing this when we are talking about caching? So when I talk about server's internal storage, access to that storage is quite fast, which is why you can use that storage for caching purpose. And for caching, you need something that is accessible very quickly. And we'll see this in a little while when we write the YAML for emptyDir. Whenever you configure emptyDir volume, you have an option to either choose the local storage of your host or even the memory of the host, because the memory is even faster. Then the third use case is temporary persistence. When you want certain logs or some files to persist temporarily, then you can use emptyDir as temporary persistent storage. Now let's go to Visual Studio Code and straight away write the YAML for emptyDir. So I'll go to Visual Studio Code here. What I've done is I've already created a skeleton of the pod. It's a simple pod. I'm naming it emptyDir-example. Then I'm creating a single container which is busybox, and the image is also busybox, and then I'm running a command that is nothing but sleep for 60 minutes as soon as container starts. Now let's add a volume to this container. So I'll press enter here. I'll indent it. I will write volumes. I will name this volume temp storage, because this is emptyDir. We know that it is temporary ephemeral storage, hence I'm naming it temp storage. I'll come here and then I will write emptyDir, and you will see this as we move with volumes. Right now we are mentioning the name, and then right after that we are typing the type of this volume. Right now we are writing emptyDir. As we progress with this and persistent storage, we'll see that this changes as we change the storage type. For example, when we discuss hostPath, it will be replaced by hostPath, and we'll see what happens when we move to cloud storage or we move to any other persistent volumes and persistent volume claims. We'll see how this behavior changes. So right now it is emptyDir because we are discussing emptyDir. Then I'll press enter. What I have done is, and you would have also done this if you are following along since the beginning, we have installed certain extensions, and one of the extensions is Kubernetes extension. If you have not installed this, you can search for extensions here and then install Kubernetes Docker and YAML extension. These will be helpful in your Kubernetes journey. So let's go back here, and because of that extension, what I can do is I can press Control space in my Mac. If you are on Windows, you can press Alt space. It will tell you what are your options that can be filled inside any of the fields. So not just for emptyDir, you can use this for all the YAMLs that we have been writing specifically for Kubernetes. Another thing is, whatever we are writing, this is not something that you have to remember by heart. You can always refer Kubernetes documentation in the exam as well, as long as you know how to maneuver through that documentation. For example, if I want to check about emptyDir, I'll go here. I will go to Kubernetes documentation. It is kubernetes.io/docs. I will just search here volumes, and it will give me the volumes. And when I come here, I can use this quick navigation to click on emptyDir. Or if you are not seeing, if this list is huge, then you can also press Ctrl F and search for emptyDir. And if you see emptyDir, then you can check what are the possible options when you want to configure emptyDir. Like we discussed, you can use local storage here and also memory. So in this, they are showing both these examples. So do not be afraid to refer documentation. And if you will not have Visual Studio Code in the exam, so you cannot just press Control space or Alt space to know your options. It is better you know how to go through the documentation. So what I'll do here is, for me, the medium is local storage, and local storage medium is the default one. So I do not have to specify medium. Size limit, if you want to specify, you can specify the size limit here, but the default is unlimited. I want to keep this default. So if you want to keep these options at default for any field, then what you can do is you can write flower braces like I mentioned here. So now it will take the default for emptyDir. What we have done up till here is we have introduced an emptyDir volume. And why we know it is emptyDir? Because we have typed here volume to this pod. Now what I want to do is I want to map this volume, or I want to mount this volume onto a container. This pod only has one container, so let's map this volume into my container. So I'll come here, I will type volume mounts. See, if you understand the foundations that what is happening, see, first you are giving the volume to a pod, and then you are mounting it to any containers that need that volume. If you understand this as a foundational concept, then writing YAMLs is a play. Just remember the foundational concepts. I'll write a colon here, I'll press enter, I'll indent this properly. What I will do is now I'll write mount path. So mount path is the path where I want to mount this volume inside the container. So what I'll say is mount this volume onto the path called /data. We have told it where to mount it. Now we have to tell which volume should be mounted. So here what I will do is mount path is this. The name of the volume that I want to mount is temp storage because this is the volume I created. If I would have created, let's say 4 volumes here, then you can see that volume mounts is a list. The first item in the list is this one, and then rest of the 4 I could have supplied here, the mount path and then the name of that volume. So you can have multiple volume mounts. For now we only have one volume mount, and this is it. Not just for ephemeral storage, you will see this format used in persistent storage as well. So as long as you understand this concept, I'm telling you it's 60% of Kubernetes storage. And then I'll add a small hyphen here so that these lines go. These lines are there because we have not supplied resource limits to our containers. Now let's remove this hyphen because we are going to apply this. And if I hover over here, you can see that one or more containers do not have resource limit. This could starve other processes, like we learned in our requests and limits section. It is always recommended to use these when you are dealing in production implementation of Kubernetes. So let's go to terminal now, and pwd, you can already see I am in day 26 of this course. If I type ls, you see the emptydir.yaml. So I'll use kubectl apply -f emptydir.yaml. I'll press enter. I will run kubectl get pods, and I can see that my pod is running. But before I do that, I said that 2 containers can share the same storage. So let's do one thing. Let me delete this kubectl delete pods emptydir. I'll delete this pods. I'll also add a force here. If you do not know what force is, I would request you to go and watch day 24. We have explained pod termination in detail in that lecture. I'll press enter. This is deleted. Now I'll go to my YAML. What I'll do is I'll just copy this and I'll create a new one here. So we are essentially creating 2 containers in this pod. Let me add a hyphen here so that this goes away for a little while, and then what I'll do is I'll name this container busybox2. So first is just busybox and the second container is busybox2. What we want to do in this demo is we want to create some file in this /data directory, and then we'll see that whatever changes we have done here, second container can also see that. And why second container will be able to see that is because emptydir volumes can be shared across containers, and hence /data or this volume will hold the writes that can be shared across both the containers. Otherwise, both these containers will have their own unique writable layers, okay, like we have seen before. But anything that they write in this /data, that writable layer will be shared between both these containers. So I'll remove this hyphen. I'll go back to my terminal. I will run kubectl apply -f emptydir. Now if I run kubectl get pods, I will see that it is in container creating state. I'll press enter. Now both my containers are running. I will now kubectl exec in, because I want to log in into the pod. I'll add -it because I want an integrated terminal. I will enter the pod name. My pod name is emptydir -example -c because I have multiple containers, and here I want to log in into my first container, which is just named busybox. Then I want a shell there. Enter. I'm in the shell. If I do ls-lthr, I will see that I have a /data folder already here, directory already here. I'll cd into this. I will echo this is my file, and then I will redirect the output into a file called myfile.txt. I'll press enter. I will cat myfile.txt. I see this is my file. I now exit this, and then I will log in into my container 2, that is busybox 2. I'll press enter. I'm inside that container. I'll do cd data. I'll do ls. I see that file already there. If I cat into that file, you see that content is also here. Instead of this is my file, we have this is my fill with a spell error. Now let's exit this. What we have understood is in emptydir, all the containers can share the storage as long as they have mounted it. So in our example, slash data was mounted onto both of these containers, and the volume that was coming from above was emptyDir. So I'll exit here and I will kubectl delete pods emptyDir example -- force. This will be deleted. I'll clear my screen. Now let's go to our diagrams and understand downward API. So what is downward API? Allows pods to access metadata about themselves. Metadata like pod's name, namespace, labels, resource limits, etc. You have created a pod and that pod has a container, and that container is running your application. Now your application is inside the container. That application does not really know anything about the pod. It does not know what is the pod name. It does not know to which namespace that pod belongs to. It does not know what are the resource limits set to that pod. And it also does not know what are the labels or anything that is associated with the pod, because it is your application. It doesn't know anything about your pod. But what if I want my application to know that? But Varun, my application is running fine. Why would I want my application to know about the name of my pod or any other metadata that is associated with my pod? Why do I want my application to do so? The reason is, let's go to day 21. In day 21, we were discussing multi-container pods, and one type of multi-container pod is a sidecar pattern. Imagine you have an application deployed and the sidecar container, the helper container, is performing monitoring. It is collecting all the metrics. But will those metrics be of any use to you if you do not know to which pods those metrics are associated with? No use, right? If I want to know what are the monitoring stats, what are the telemetry stats, for example, of application 1 namespace, if I do not know what all pods are part of application 1 namespace, can I provide that data in a meaningful way? I cannot do that. So to have such kind of scenarios, it's not your application that requires pod name or pod namespaces, but so there could be certain corner use cases where our application requires that, but the things that are helping your application, for example, monitoring, logging, these things will definitely need the name of the pod, the namespace, or any other things that you want to have. So in that scenario, you can use downward API. And when you are using a helper container for performing monitoring, logging, they often use downward API volumes to present that data to you. So if I go to day 26 again, which is our today's topic, we see that this metadata can be injected using EVs, that is environment variables, or files as volumes. And we'll see that in the demo, both how EVs and volumes behave. Third point says offloads the API server. So if I want to check the pods that are running on my system, I just run kubectl get pods. Unfortunately, I do not have any pods in the default namespace, hence I do not see anything. But if I add -n kube system here, I would know what are the pods that are running in kube system namespace, and that is how I know the names of these pods. If I run kubectl get namespaces, then I know what all namespaces exist in my Kubernetes cluster. Now, if for example, my container wants to know what all namespaces exist, what is the name of my pod, then it should be able to query the API server to have that information. Because if I want to have that information, I am using my kubectl client, and that kubectl client is querying the API server to have this data. So if you look at day 7, we learned the architecture of Kubernetes here, and we also discussed the deployment workflow. What happens when you create a deployment? So whenever you type a command via kubectl, it first goes to the API server, and then API server displays the results to you. There are several other things that are done by API server. There are more functionalities to it. But right now, if you query something, then API server is the one that returns the results to you. If, for example, you didn't have downward API, then all your queries would have gone to the API server. So if my container wants to know the pod name, then the container would query the API server. Now it could be an HTTP request to the API server, and then you will also have to configure authentication and all these things, because you cannot access a cluster until and unless you provide authentication and authorization information. So there's so much to it. So if downward API weren't there, then your application or your helper container would be querying the API server continuously, and we don't want that. API server has several other responsibilities. We don't want to overburden it. Hence, using downward API, you are essentially offloading the API server. So what are the use cases of downward API? The first is dynamic configuration. For example, you have configured logging and monitoring. You do not have to specifically go and hard code or do any sort of coding to tell the helper container that this is my API server. You go to this API server if you want to fetch any information. We don't have to do that because we have downward API, which is already providing that data to you. Self-awareness. Whatever my container is collecting some logs or it is monitoring my pod, that helper container is already self-aware that the pod that I am part of, its name is this, the namespace is this, labels are these, and these are the resource limits. Extremely helpful if some application owner comes to you and tells you that, hey, I want my application to have this data. We don't know why their application wants it. That can be part of a discussion. But if an application owner comes to you, then you have a solution for them. You can always use downward APIs. Let's go to, where do I have to go? Yeah, Visual Studio Code. So I already have pre-created YAML for you. I will go to downward API 1. I'll add a hyphen here so that it eases our readability. What we are doing is, its kind is pod, its downward API hyphen example is the name of the pod, label is app is equal to demo. Then we have only one container in this, and that container is called metadata container. This container is just running a command called env. Env will display all the environment variables that are associated with your pod, and then we are saying sleep for 60 minutes. This we are seeing for the very first time. This is a way of defining environment variables in your pods. We'll be looking at this in detail when we discuss ConfigMaps and secrets, and that will happen soon in next lecture. So what we are saying is, we are saying env. Env is a list, which is why you can have multiple environment variables. The first environment variable that I am creating is called pod underscore name, and I am saying that the value from field reference field path is metadata dot name. So I am saying the name of the environment variable is pod underscore name, and the value for that you pick it from metadata dot name, and metadata is this and name is downward API hyphen example. So when we run this YAML and we check the logs of the pods, we should see that the pod name is filled as downward API example. Similarly, pod underscore namespace is our second environment variable. Its name is pod underscore namespace, and then the value for this will be metadata dot namespace. So metadata is here, namespace is not here. But when I run this pod, when I apply this YAML, this pod will be part of the default namespace, and the default namespace's name is default itself. So I should see that pod underscore namespace is default. Now metadata dot namespace, this is a new format that we have seen in as we progress with the course. In the later lesson we'll discuss about JSON path, and there we'll discuss this in detail, but for now it's very primitive to understand that metadata dot namespace, it will look for metadata, and inside that it will look for namespace. So I'll just remove this hyphen and I'll save this. Oh, it's getting auto saved. So I'll go to the terminal and I will run kubectl apply -f. The name is downward API 1.yaml. I'll press enter. It says it is created. So if I run kubectl get pods, I see that this pod is running. And I also want to show you something else. If I run kubectl get pods downward API -example -o YAML, this will give me the YAML of this pod. So if I do this and if I scroll above, I want to show you namespaces. Default this is auto-filled and this is under the metadata section. Okay, now I'll clear my screen. What I'll now do is I'll again run kubectl get pods, kubectl logs. I want to check the logs of this pod. And if I press enter, you see here we have a pod underscore namespace is default. We see that this environment variable is created and then pod name environment variable is also created. So that's one use case that you can perform. Then let's discuss the second use case. So if I go back to Visual Studio Code, I will open downwardAPI -2 here. And here also we are doing something similar. The first use case we saw used environment variables. This use case will be using files which will be mounted as volumes. So I'll quickly add a hyphen here so that I get rid of these lines. Here as well, I'm creating a pod. The name of that pod is downwardAPI -volume. Then I'm adding couple of labels. App is good app, owner is HR, annotation version is good version. What I'm doing here is I am running a command that is catting any files that are available in pod info directory. So let's first discuss the volume part so that you can understand this part in a better way. Always when you are discussing Kubernetes storage, if you're troubleshooting any issue, first check the volumes and then see which containers are using that volumes, or you can reverse engineer. Go to the container which has a problem, for example, which you are troubleshooting. You see the volume mounts, you see that, and then you go to the volume associated with that volume mount, because you always see a name here. Anyway, so let's first discuss this. We are trying to run, we are learning to walk right now. So we have volume section, and under that volume section we only have one volume. That volume is named downwardAPI -volume, and this is the syntax. Okay, now what I'm doing is downwardAPI has items. The item, this path is important. I'm saying path is labels. So labels is the file that will be created that will hold the values in metadata.labels. So what will metadata.labels give? Metadata.labels will give app is equal to good app and owner is equal to HR. So this file, when this file is created, it will hold all the labels. Then we are creating a second file. So you see the path is files, and then we are creating another file which is called annotations, and this file is referencing the field path metadata.annotations, and metadata.annotations is version is equal to good version, and this is the current annotation that we are adding. But Kubernetes also adds certain annotations which we will see once we implement this YAML file, once we apply this YAML file. So I hope this is understood. Now let's do one thing. Right now I am calling labels and annotations, but as we have seen in our diagrams, you can know the namespace, resource limits, and there are so many things. I'll let you read the documentation for it to understand it further, but let's for now implement this YAML. I'll go to my terminal. I will write kubectl apply -f downwardAPI -2.yaml. I just quickly want to verify one thing. I'm calling the previous one downwardAPI -example. Let me see what is this pod. This is called downwardAPI -volume. So this should work just fine. I was saying maybe it will create a naming conflict and it will not allow me to create this pod. Let me press enter. It has created this. Now I will run kubectl get pods. Now you see that downwardAPI volume is running. I will run kubectl exec -it. The pod name is downwardAPI -volume. This only has one container, so I do not have to supply -c. If it had multiple containers and I wouldn't have supplied anything, then it would have taken me to the first container by default. So I will run this and then I will take a shell. I will now directly go to cd etc pod info. I'll directly go here, cd etc pod info. If I run ls here, you see annotations and labels are two files created, ls-lthr. These are symlinks. So what I'll do is, if you go here, you see that we said that name create two files with the names, labels and annotations, and these files should be dumped onto etc pod info. So essentially what we are doing is we are mapping these files in this directory. So that is what we are doing. So I'll go here, I will do a cat on annotations. You see all the annotations here. You can see that version, good version. And as I said, there are some annotations that are added by Kubernetes itself. So other annotations are associated with that. And then I can also run cat labels. This will show me both the labels. App is equal to good app and owner is equal to HR. Now I can exit this container. I could have also seen this using kubectl logs command. So kubectl logs, if I check the logs of this pod and I press enter, you can see this in the logs as well. I hope this is understood and you will be using this quite a lot in your production implementations. I'll go back to my diagrams, and the last thing I want to discuss is ConfigMaps and secrets. Now before I discuss them in detail, the first thing I want to mention is ConfigMaps and secrets are extremely important, not just for your exam but also for your interviews and your production implementations, because they are used all the times. ConfigMaps and secrets inject configuration and sensitive data into pods. So ConfigMaps can be used to inject configuration and secrets can be used to inject sensitive data into pods in Kubernetes. They allow the decoupling of configuration from application code. Now, what exactly does decoupling mean? So we have been discussing this since the inception of this course. In day 11, we discussed the benefits of microservices. We started with a monolith architecture and then we upgraded that architecture into a 3-tier design that you see here. We segregated the tiers into front end, back end and database, and then we again improved that design by introducing something called microservices. But at every stage, the important thing that we discussed was your application code or your container image should only hold the code of the application. For example, if I am in my application tier, then my application tier should only have the logic of the application tier. Authentication, authorization, API communication, logging, caching. These things should not be handled by the application tier. These things should be separated. Now, then we move to day 12. In day 12 as well, what we saw was our front end deployment wanted to speak with our back end deployment. So at that point of time, what we said was each pod, when wants to initiate communication with the backend deploy, will be sending the traffic to the backend service. But do I have to code the backend services URL into my application logic? Because this backend services name could be changing all the time. This could be this name in this deployment, in another deployment this could be named something else, in another environment this could be named something else, and so on. I do not want to hard code this into my application logic. So what I can do is I can tell the application logic, if you want to reach the backend, you look at this file, and this file that I am referring to is something that will be injected into the container using ConfigMap. And similarly, secrets can be used to inject certificate or any other secret data. And we'll be discussing this in greater detail in next lecture. And I want you to pay attention to the storage section entirely. So if I go to my browser and I go to the curriculum of CKA, whatever we are discussing in past 3 or 4 lectures is very important, because this holds 10% of weightage in the exam. So you see the curriculum, whatever we have discussed thus far, this will play an important role. So make sure you learn these concepts. I think that's all I wanted to cover. Before I start this lecture, I have a request. If you are finding my content useful, then do like my videos, subscribe to my channel, and drop a comment. Even if it is just a hi or a thank you note, it does more than you know for me. Now let's get going with the lecture. Persistent storage. What is persistent storage? So anything that prevails irrespective of the lifetime of the pod is persistent storage. For example, if I have connected a USB drive to my laptop, and if my laptop crashes, God forbids that happens, the data in my USB drive will still survive. Similarly, if I have a pod and I attach a volume to that pod from an external storage system, then even if my pod dies, that volume, that storage will still exist. So let's now discuss how persistent storage evolved in Kubernetes. I want to go to day 25, where we discussed that Kubernetes has a core, and then there are things that are not part of the Kubernetes core. The core of the Kubernetes is container orchestration. Anything else, like how the underlying networking is handled, how the storage is handled, or how the containers are created, removed, these are not part of Kubernetes core. There are separate plugins, add-ons, and third-party extensions which can be used to enhance the capabilities of Kubernetes core. But there are things that are separate. In today's lecture, we'll be discussing storage, which is a separate part and is governed by CSI. So persistent storage. So there are two ways via which you can have persistent storage introduced into your cluster. First is the entry drivers, and the second is CSI backed. Entry drivers are now deprecated. Historically, storage drivers were embedded in the Kubernetes core. So if I go to day 25, here we discussed what is the Kubernetes core and what are the extensions that are used to extend the capabilities of the Kubernetes core. Kubernetes core is essentially your control plane components and the node components. So the community, the Kubernetes community, actively works on development of items that are part of the control plane and the node components. However, anything else, the list that you see here is just indicative. There are many more plugins, add-ons, and third-party extensions that are used to enhance the capability of your Kubernetes cluster. For example, the Kubernetes core says, I have defined certain interfaces as in CNI, CSI, and CRI, where I define this is how networking, storage, and container runtime should look like. As long as you adhere to the standards that are defined in these interfaces, you can have your own networking, own storage, and own container runtime. Hence, there are multiple organizations who have come up with CNIs, CSIs, and CRIs. And similarly, there are different add-ons that can be integrated into Kubernetes cluster. There are third-party extensions as well, as you see here. What happens is Kubernetes community is the one who will set the standards for CNI, CSI, and CRI, and then Kubernetes community is governed by CNCF. Hence, we say that Kubernetes is a CNCF project. And it is not just Kubernetes that is part of the CNCF project. There are many more projects under CNCF like Prometheus, Istio, Envoy, etcd, Helm, CodeDNS, and there are many more. And most of these tools you will be learning as you progress with your DevOps journey. But why are we discussing this now? We are discussing this now because historically storage was integrated into the Kubernetes core itself. There was no concept of CSI, and at that point of time entry drivers were prevalent. There was a problem with entry driver. Understand that if you have integrated storage right in the core of Kubernetes, and we know that there are various storage vendors, there is NetApp, there is Dell EMC, and then you have cloud storage options. It is not possible for Kubernetes to take care of everything. And even if, let's say, AWS writes their own entry drivers, it still must be integrated into Kubernetes core. And if you integrate that, for everyone to use those drivers, there must be a Kubernetes upgrade so that you can use those drivers. Hence, whenever there was a new storage vendor, or there were new features, or we had to remove certain bugs from the existing entry drivers, then it was a mandate that the entire Kubernetes version must be upgraded. Now, this is not an efficient way to do things. We want developers and storage vendors to work independent of the Kubernetes core. If they introduce a new feature, then I just want that feature to be upgraded. And if I want that feature to be upgraded only, then CSI is the way to go. If I'm using a previous version of CSI, I introduce a new version which has all the new features. For example, Amazon releases a new version of CSI driver. That driver has a volume expansion. Now, to have that feature, what I will do is I'll just upgrade the CSI driver and I can use the volume expansion feature. Now, entry drivers, you would still see them used, but all the modern implementations of Kubernetes will have CSI. Now, if you as an administrator have an option whether to use entry or CSI, then you should pretty much always choose CSI, because the development of CSI is done actively by the storage vendors and the community that takes care of that particular CSI driver. Now, before I move to the next section, I quickly want to show you what are the examples of entry drivers, and we'll also look at documentation where we clearly see that these are now deprecated. So examples are AWS EBS, Google Persistent Disk. But Varun, these are modern things which are available in cloud providers now. Why are they deprecated? I want you to understand that we are not saying that these storage systems are deprecated. We are just saying the way these storage systems were accessed has changed from entry to CSI. Entry was something that was embedded into the Kubernetes core, and it defined if you are using entry, then if you are mounting an EBS volume using entry drivers, then that part is now deprecated. So if I go to the Kubernetes documentation and I search for volumes here, I go to volumes, and if you look at the index on the right, you see Elastic Block Store deprecated, Cephs deprecated. So these are now deprecated. The latest and greatest is CSI. Now, what is CSI? Like we discussed, CSI is a standard that is set by Kubernetes community. Anyone who adheres to that standard can write their own plugin, and that plugin can be used by Kubernetes to access the respective storage system. Check the provisioner field in the storage class to confirm. Now, how do I know whether I'm using entry drivers or CSI backed? We have not discussed these terms yet. What is capacity, access mode, storage class? We have not discussed these. But I want you to know this, that you can always check whether you are using entry or CSI backed. In entry, you would always see the name directly here, AWS Elastic Block Store, and in CSI backed, you will always see something like CSI, and then you will see the provisioner as well. Here the provisioner is ebs.csi.aws.com. So that's the differentiator for you. CSI backed are available for both file and block storage. Now, what is file and block storage? file storage is something that you will be mounting onto multiple Linux system. For example, if you have 10 applications and all those 10 applications want to access a common file share, then you would be using file storage to allow multiple systems to access the same share, and they could be reading data from it and they could also be writing data onto it. What is block storage? Block storage is typically accessed by a single system. For example, if you have a laptop and you attach a USB drive to it, it is only your laptop who can access that USB drive. It's private to your laptop. Similarly, block storage is typically used by a single system, and I'm using the words typically and usually because there are always corner cases where there would be a file share that is only accessed by a single system and a block storage that is accessed by multiple systems. But in typical use cases, file shares will be accessed by multiple systems. You will be using file share when you want to give multiple systems access to a shared storage. You will use block storage when you want to attach a separate storage to your pod or to your laptops. Now, examples of block storage could be your databases, transactional system, and file storage could be any shared workloads. Maybe your web servers want to access a common share, so use cases like this would be using file storage. Now, there are CSI drivers available for both file and block storage, and whenever I'm saying CSI driver, do not limit yourself to think that these are only available on cloud providers, not on premises. There are multiple CSI drivers that are available for both on premises and for cloud deployments, and they are not only available for file storage or block storage, they are available for both. For example, if you are working on Amazon, there is a CSI driver that you can use to access the file storage on AWS, which is Amazon EFS or Amazon FSx, and you also have CSI drivers that can be used to access the block storage from Amazon, which is Amazon EBS. If you see the examples here, AWS EBS CSI driver, GCP persistent disk CSI driver, vSAN CSI driver. If you are into Broadcom's ecosystem, then you can use this on premises. Then there is Portworx CSI drivers. You could be using this when you are using an on-premises storage, and there are different storage vendors like NetApp, Dell EMC. They will have their own CSI drivers for both file and block storage. Then Varun, what about object storage? How do I access my object storage from my pods? Do we have CSI drivers for that as well? So what is object storage? Object storage has a flat architecture and you can access the files using URLs or REST. Then how do I access object storage? Firstly, object storage is not supposed to be mounted onto your pods. If I talk about file and block storage, this can be mounted, but object storage is not mounted. What you can do is your pod can make API calls to access the object storage, or your application could be using SDKs that are available from different vendors to access their object storage. So if you want to access Amazon S3, then you would have an SDK and you will configure that SDK along with your application, which will help you access that object storage. The command that you can use to check your CSI drivers is kubectl get CSI drivers, or you can look at the storage class, which is SC, or PV, which is persistent volume. Both SC and PV we have not discussed yet, but if you run kubectl get PV and the name of the PV, then you can know which CSI drivers you are using and also confirm whether you are using CSI drivers to begin with or not. If I have to summarize this section, I would say that earlier Kubernetes supported a lot of built-in drivers called entry plugins, but today the ecosystem has fully moved to CSI drivers, which are a future-proof way to provision and consume persistent storage in Kubernetes. So whatever storage you are dealing with, AWS, EBS, NFS, iSCSI, Fiber Channel, if you are doing it the modern way, you are doing it with a CSI driver. Let's now move to the next section, which is hostPath. Now hostPath is a type of persistent storage, and hostPath is a special use case. Why is it a special use case? It's a special use case because hostPath uses entry drivers and there are no CSI drivers available for hostPath. hostPath is not a recommended way to create volumes in Kubernetes. Kubernetes does not recommend it. Why it does not recommend? Because hostPath uses the underlying storage of your node, and when you use the underlying storage of your node, you are essentially creating a directory in your node and then sharing it with a pod. If that pod is malicious, it could do certain things in your directory which are not permitted. Hence, Kubernetes says it is a security concern if you use hostPath volumes in your production environments. Hence, you can use it for testing, and if you have tight controls, if you have only given the permissions that are needed, then they will not pose a risk. But you must understand that Kubernetes does not recommend using hostPath in production grade environments. Now the first line says mounts host node files or directories directly into the pod. So this is what we defined right now. If there is a directory in your node, you can directly share that with the containers in your pod. Similarly, if there are files, you can also map those files as volumes onto your containers. I have this diagram here, and I have put this here to explain you what exactly is the host nodes storage. Because if you are on cloud, let's say your worker node is running on an EC2 instance, then that EC2 instance storage will be called the nodes storage. So if you have a pod running on, let's say, that EC2 instance, then that pod can have files or directories mounted onto it using the hostPath volume. But we are using Docker desktop, hence it is an important distinction I want to make. When it comes to Docker engine has an architectural caveat which only allows Docker engine to be configured onto a machine that has the Linux kernel, and macOS and Windows do not have a Linux kernel. So what Docker has to offer is Docker desktop. So what we have done is we have installed Docker desktop, and when you install Docker desktop, a lightweight Linux VM is configured for you, and that lightweight Linux VM has the Docker engine installed. And we are using Kind to create Kubernetes cluster. Kind is Kubernetes in Docker. Hence, our Kubernetes cluster is essentially comprised of 3 nodes, and all those 3 nodes are running as containers. So the first one is control plane node, then we have 2 worker nodes. Any containers that run are running on worker node 1 or worker node 2. Control plane is running control plane components. When I create a pod on top of a worker node, then the underlying host storage for that pod is the storage offered by this worker 1, this container, and this container is indirectly using the storage from this lightweight Linux VM, and this lightweight Linux VM is using the storage from a Mac OS. The underlying storage is still Mac OS's storage, but the nuanced difference is worker 1 container is giving the storage to the pods that are residing on worker 1. If you have installed Docker engine directly onto this, let's say, an Ubuntu VM, then your Ubuntu VM's storage is called the host storage. That's a nuanced difference. In summary, if you are using Mac OS or Windows, the node storage is provided by this container, And if you are using Ubuntu, then the host storage is provided by this worker 1. Persists beyond the pod's lifetime as it maps to a path on the host node's file system. This is understood. If something is lying on your host node, then that will not be deleted when the pod is terminated. Enables data sharing between containers in a pod and across pods in the same node. This is an important distinction. When we were discussing emptyDir in our previous lecture, we said that all the containers part of the pod can access that emptyDir volume. But with hostPath, we are saying all the containers in the pod can access that volume, but also any pods that are residing on the same node as the node which has the host path volume can also access that. So understand it this way. Host path volume, if we are using this worker 1 for example, we have created the host path volume here. So any pods that are created on this worker 1 can access that host path volume. Then what are the use cases for host path? Use cases are, you can use this for scratch space. What is scratch space? Scratch space is a temporary storage that your pods can use. Then caching. The underlying storage with the host is usually pretty fast. If you want to use that for caching purpose, you can use it. Now, there are niche use cases where you may want your pods to access the host logs. So what you can do is, you can map the host logs directory onto your pod so that your pods can access host level logs. Again, I'll mention, if I go to the documentation of this and I check host path, then you would see using the host path volume type presents many security risks. If you can avoid using host path volume, you should. Let's go back to our diagram. And now let's go to Visual Studio Code and do a demo for host path. So I'll go here, day 27, and day 27 has already a skeleton YAML for a pod. I have not added any host path characteristics as of now. So let's add the fields associated with host path. So what I'll do is, I'll first create a volume, a host path volume, and understand I'm not doing anything separately. A host path or emptyDir is created within the pod manifest itself. You do not have to define them separately anywhere. What I'll do is, I'll add a volumes section and then I'll name this volume host volume. Okay, then I will mention host path. And we learned yesterday that under the volume section, you type the type of volume that there is. Okay? We are creating a host path volume, which is why we are writing host path here. So I'll add a colon, press enter, indent it, and then I will write path. Now what I'm saying is, the name of the volume is host volume and the host path, as in the path in my host where this file or directory is, this I'm saying host file. Now what I'll do is, I'll press enter, type. This is an important part. Here I will write file or create. So what I'm saying is, if this file does not exist, then create this file. So in case my host system didn't have this file called host file, then this would have created. Now since we already have host file, for example, let's say if you had this host file, then you could have just written file here. So let's go to the documentation and look at what other types are available at your disposal. Yeah, so these are the types that are available: directory or create. It's simple that if the directory does not exist, it will create it. Directory, if you already have the directory, you can just use this. File or create we have just discussed, and file we have also discussed. There are few more types that you can see and use as appropriate. I'll go to Visual Studio Code. Now what I have done is, up till here I have introduced a volume to my pod. Okay, but what I have not done yet is, I have not mounted that volume onto a container. This is an important concept and this should stay with you. First you introduce a volume to a pod or multiple volumes to a pod, and then you have to map those volumes onto containers. So this is a very good way to do things. So if you have a volume and let's say you have 3 containers, you can choose to only map that volume onto a single container if that is what your requirement is. So let's do one thing now. We have one container in this pod. Now let's map this volume onto this container. I'll simply write volume mounts, because here we are creating the volume and here we are mapping the volume, which is why you see here volume mounts. And where do I want to mount this volume? What is the mount path where I want to mount this volume? The mount path for that is /data. Let's say here is the place where I want to map this volume or mount this volume. And what is the name? Here the name is, what is the name of the volume that I want to mount? I want to map the volume with name host volume. So I'll write here host volume. That's it. We are done. So let's do one thing. Let's save this file. Let's go to our terminal, and I am already in day 27. I will now write kubectl apply -f hostPath.yaml. So I have that created. If I run kubectl get pods, I will see that there is a host path example pod running. There are 2 more pods. These are from our previous lecture. So if I run kubectl get pods -ovide, I know that this pod is created on my second cluster worker 2. So the next pod that I will create for testing will be on this node. So I'll just copy this name so that I can use it later. And then what I will do is I'll run kubectl exec to go inside the pod or to run commands onto this pod. Then I'll write -it. -it is give me an integrated terminal, because I want to go into the pod and then insert some data into that file it. And then what I'll do is I'll name the pod. I'll write the name of the pod, which is hostPath -example. Then I want to run bin sh. I want a shell. So I am inside the pod now. If I run ls, you see that there is /data. Since we are mapping a file, that file is mapped on the mount path /data. So if I go here, I can just do vi data, because data is a file. So if you see here, we have mounted host file onto the path /data. Now if I vi data, I can insert here, this is my file, do not touch it. Again, it's fill. Let me write file, and then I will save this. If I cat data, you see that this is my file, do not touch it. What I'll now do is I'll go in Visual Studio Code and I want to create one more pod. So I'll call this pod hostPath example2. Let's edit the same YAML. And here I will add one more property, and that property is node name. Node name is I want this pod to be manually scheduled onto this worker node. Then I will save this. I'll go back to my terminal. See, all the volumes and the mount path for this pod will also be same as of our previous pod. And ideally, since the data in the host path volume can be shared amongst all the pods that belong to the same node, we should be able to access this data. So let me go back to my terminal and let me apply this file kubectl apply -f hostPath.yaml. It says that the pod is created. I'll run kubectl get pods and I see that the pod is in a running state. Now I will run kubectl exec. I won't add a -t this time because I will be running the command from this itself. I'll write hostPath example2 and then I will write cat the file data, and you see our data is available in here. And let's do one more thing. If I create another pod here, let me call this 3 and let me create this onto worker 1, and worker 1 is just called worker, I think. Yeah, it's just called worker. So I'm creating this in worker. Ideally this should not be able to see any data that is here. I will run kubectl apply -f hostPath.yaml, and let me also change the pod name is already changed. I'll press enter. it is created. If I run the same command and here I will write example3, then you see it is not able to display anything because that data is not here. As we mentioned, the pods can access the data as long as that pod resides onto the same node. So the previous two pods that we created resided on worker 2, which is why they were able to access the host path volume, and this pod is not able to access because we have created this in this worker. If you see kubectl get pods, this one was created, the third one was created in only this node, worker node, and our previous two pods were created in worker 2. I hope this is understood. I will now clear my screen. I will delete these pods, kubectl delete pods, host path example, host path example 2, host path example 3, downward API as well, I don't want that, example, and downward API volume. I'll also add a force here so that the pod object is deleted immediately. I'll press enter and all of them are deleted. I'll now go to my diagrams again to discuss the next topic, and this is a meatier topic. What are PV and PVC? Forget PV and PVC. Let's first discuss what is happening with the diagram. So we have a physical storage. Now this physical storage could be your SAN storage, and then this is your Kubernetes cluster. Your Kubernetes cluster has a pod, and that pod has two containers. We have a PV here and we have a PVC here. What is PV? PV is a logical abstraction of the physical volume. So what, Varun? If you talk about a Kubernetes cluster, like I told you, there must be a physical storage somewhere available, and then that physical storage is mounted onto your Kubernetes cluster. So if I talk about this diagram, there must be a physical storage that should be providing this 5 GB. Hence, PV is a logical representation of the storage that you need. And what is PVC? PVC is persistent volume claim, and persistent volume claim essentially claims a persistent volume. The relationship between PV and PVC is 1-to-1, which implies only one PVC can put a claim on a PV. Then what happens is, then you have a pod. A pod can call this PVC, and any storage that is available in this PV can be accessible to this pod. So once that pod has that volume, any containers part of the pod can map that volume. When you schedule a pod onto a node, then that pod uses the resources of that node. For example, if this pod requires 1 vCPU and 4 GB of memory, then this pod is taking those from this node. Similarly, when you have a PVC, PVC will use the actual physical resources available with the PV. For example, here we are creating a PVC that is requesting 2 GB of storage, and when you make that request, this PVC will be using 2 GB provided by this PV. Like this pod was using 1 vCPU and 4 GB provided by this node. I hope this clarifies the difference between PV and PVC. Now let's see the entire workflow, how it happens. I have deployed my application onto a pod, and that pod has 2 containers, and my application requires 5 GB of persistent storage. What the flow will be? I'll go to my Kubernetes administrator because I am the developer. I'll ask my Kubernetes administrator that I want a 5 GB volume. My Kubernetes administrator will coordinate with the storage admin, because storage admin is the one who is managing this physical storage, and storage admin will create a 5 GB volume. Since my Kubernetes cluster already has CSI plugin installed, my Kubernetes cluster can interact with this physical storage. Then Kubernetes administrator will create a PV of 5 GB. Then I'm saying Kubernetes admin or developer creates the PVC, because this can be an overlapping role. In most environments, I have seen Kubernetes admins taking care of everything from end to end, but there are scenarios when you would see developers are the ones who are creating the pods and PVCs for themselves. You as an admin will only have to take care of PV, and as we progress with the course, we'll see that the role of PV will also be automated using storage classes. Developer calls the PVC in the pod deployment manifest. So once the PVC is there, developer can call that PVC to have this 5 GB storage associated with the pod, and then developer has a choice. Developer can mount that volume onto both of these containers or onto a single container. That is the entire workflow of PV and PVCs. Now let's evolve this architecture further. If I move down, we have the same diagram. What I have done is the PVs are here. There are multiple PVs of different sizes, and then there is an application one namespace here. But why we are mentioning namespaces? So let me go to the terminal, and if I run kubectl API resources, it will tell me all the Kubernetes objects that are available at your disposal. If I scroll at the top, I see there is persistent volume claims, and then there is persistent volumes. You see here persistent volumes are not namespaced. If something is not namespaced, it implies that it is available to the entire cluster. For example, nodes are also, you see, namespaced is false because nodes are available for the entire cluster. Similarly, persistent volumes are available for the entire cluster. However, persistent volume claims are namespaced, and the pods are also namespaced, as we have seen in our previous lectures. So both pods and persistent volume claims are namespaced, but persistent volumes are not namespaced. Now, why does it matter? So let me go back to our diagram. If let's say there is a pod in application 1 namespace, and then that pod has requested for 5 GB of volume. Now I would have created a PVC, and in that PVC I would have defined that this PVC is part of app1 namespace, because if you create any resources and you want those resources to be part of a specific namespace, then under the metadata section you define the namespace. For example, if I would have wanted this pod to be part of a different namespace, I would have defined a namespace here. If pod has claimed this PVC and this PVC is bounded to, let's say, this PV, then understand that this PVC cannot be used by any pod that is not part of this namespace. If there are multiple pods in this namespace, they can access this 5 GB volume just fine. If your use case wants other pods to also access that volume, that is possible, but you cannot have application 2 namespace access this PVC. And remember what I told you in the previous section. I told you that there is a one-to-one relationship between PV and PVCs. If this PVC is consuming this PV, then any other PVC, even if it wants 5 GB, it cannot be bounded, it cannot be associated with this PV. Hence, there is one-to-one relationship. I hope this concept is understood. Let's move to the next section. So we have the same architecture. We have a physical storage, then we have a 5 GB PV, we have a PVC, we have a pod, and then we have a single container. The flow is pretty much the same like we discussed before. So first, let's say what happens. Developer requests for a 5 GB volume. I, as an administrator, create a persistent volume. So the persistent volume, the kind is persistent volume. The metadata, I'm naming this volume example PV. The capacity of this volume is 5 GB, and our storage admin would have given us 5 GB of storage. And then there is something called access mode. Access mode is read write once. What does access mode mean? Access mode essentially govern how the volume is mounted across nodes. So whenever I say access modes, I want you to think in terms of nodes, worker nodes, not pods. So let's go to the GitHub repository and let me scroll down, and here you see access modes. There are 4 types of access modes that you would often see being used. What are these access modes? When I say read write once, I want you to think from a node perspective. The volume can be mounted as read write by a single node. Read write once by a single node, and then once it is mounted onto a single node, then multiple pods can access that volume in the same node. So whenever you see once, think of block storage. Whenever you see many, think of file storage. So if your pod wants to access block storage, and block storage we know are typically used by databases and high transaction systems, then the access mode will use once. And why is that? Because like we talked before, block storage is supposed to be accessed by a single system, whereas file storage is supposed to be accessed by many systems. What is read write once pod? Read write once is similar to this, but only one pod can access that volume. And this was recently introduced in 1.29 and we are on 1.32. And then you have read only many and read write many. Read only many, the volume can be mounted as read only by multiple nodes simultaneously. If a volume is mapped to multiple nodes, then think multiple nodes can have multiple pods, and all those pods can be accessing that volume. Read write many. Similarly, here only read access was there, and here we are saying both read and write access. The volume can be mounted as read write by multiple nodes simultaneously. Just go through these because these are important concepts to grab. Access mode is read write once. Here we understand that this volume can be used by a pod that resides on a specific node, and then there could be multiple pods that are accessing that volume. Host path is path /mount/data. In actual production use cases, you would have the name of the actual storage here. So if I move above, here you see there was this actual name of the storage, and here we were using CSI, so actual name of that storage was there. But since I am on kind cluster, hence I am using a path that is shared from my local nodes storage itself. That is why I'm saying host path here. Then the next one is persistent volume claim. So once the persistent volume is created, you create a persistent volume claim. Persistent volume claim is an essential item, because if access mode I do not read write once, which is same as the persistent volume, then this persistent volume claim will not be able to bound with persistent volume, because the access mode should be same. Only then a PVC will be able to bound with a PV, and there are few more conditions which we'll see later in this lecture. Then what resources I am requesting? I am requesting for 2 GB of storage, but this one is a 5 GB. I am requesting only 2 GB here. Even then the bound will happen, because when it comes to storage provided by PV should be equal to or more than demanded by a persistent volume claim. So here if I am saying 2 GB but the volume I have in my cluster is of 5 GB, then also persistent volume claim will be able to bound with this persistent volume. And then I have a pod. If you see, pod is calling this volume here. Pod is saying the name of the volume is persistent storage, and the persistent volume claim I want to use is example PVC. You see the correlation? It is calling the PVC here, and once the PVC is called in the volume section, then I can mount it onto any of the containers part of this pod. And here you see the volume mount. The mount path is this, because this is where I want to mount this volume, and the name of the volume is persistent storage. Just taking it from here. I hope this is understood. Let's see the next flow. Next flow is also similar. Now why I'm showing you these flows is I want you to understand the options that you have available here one by one. I do not want to bombard you with everything in a single place. Now in the next one, what we have done is we are using AWS cloud for storage, and then we have a Kubernetes cluster. Now this Kubernetes cluster could be onto EC2 instances, or this could also be Amazon EKS. Same thing, we have 5 GB volume PV here, a PVC pod with 10 GB volume. This should also be 10 GB, please pardon me. Yeah. First we create a persistent volume. This persistent volume says capacity is 10 GI, which is why you see a 10 GB volume is created. Then the volume mode is file system. What is volume mode? Volume mode is whenever Kubernetes present this volume to your container, it will format it into a file system. For example, here the file system type we have defined is ext4. So whenever this container will see this volume, it will already be formatted with ext4 file system. But the other option you have with volume mode is block. So when you use the volume mode as block, and do not confuse this block with block storage, okay, this is different. So whenever the volume mode is block, the volume that will be presented to the container will not have a file system, and that container will have an option to format it as per its liking. So some of the Oracle and Mongo databases would want a volume mode as block. This is again dependent on use case. So if you have used VMware products, you would have heard of raw device mappings, RDMs. So RDMs were similar to this. You wouldn't format RDM with VMFS file system, which was VMware's file system. You would present RDMs directly into the OS, and OS would format that as per its liking. Similarly, you have volume mode block, which can be used if you want to provide the volume as a raw volume. Then access mode we have already discussed. Then there is persistent volume reclaim policy. Persistent volume reclaim policy defines what happens to the physical volume if the persistent volume claim is deleted. Should I be retaining it? Should I be deleting it? So let's look into different persistent volume reclaim policies, and these are often called reclaim policies. Let's just go here. I'll scroll down a little, and here you see reclaim policies. Reclaim policies, the first one is delete. Delete implies when this PVC is deleted, you also delete the corresponding persistent volume. Retain implies that when I delete the PVC, you retain the PV, and you would be using this when you want to audit the data and when you want to check the data. But when I talk about any cloud implementations of Kubernetes, you would often see that delete is being used, because when you delete the pod and the PVC, you also want the PV to get deleted, because in cloud you are paying cost as you use, and EBS volume has a cost associated with it. Common for dynamically provisioned storage, which is often you would use dynamically provisioned storage when you are on a cloud provider, and we'll see what dynamically provisioned storage is in a later section. There is also recycle, which is now deprecated. Recycle would essentially run rm-rf in your volume and delete all the data. Now there are modern methods available like retain and delete, hence recycle is no longer available, because recycle was also removing all the data manually. Instead of this, you can delete the volume and then recreate it. Let's go back to our diagrams now. Then we see a storage class name. Storage class we'll discuss in a little while. Then you see CSI. This is the part we all love. We want our storage systems to be accessed using a CSI driver. Here I am using an EBS CSI driver. I am saying the volume that this PV is associated with, its ID is this, and this is a volume that would actually exists in your AWS cloud with the ID as mentioned here. And then we are saying that the file system type is ext4. Now if I want a persistent volume claim to be associated with this persistent volume, then I would want to have these characteristics defined in my PVC as well. So for example, access mode read write once, I have read write once here as well. Here I am requesting 10 GB of storage, and this PV has 10 GB of storage. Volume mode is file system, and volume mode must match. Access mode must match for the bound to happen. If you see, volume mode is file system, and here also the volume mode is file system. Volume name EBS CSI PV, and here is the volume name EBS CSI PV. I am asking this persistent volume claim to only look for volume whose name is this. If this would have not existed, then the PVC would remain in pending state. Then storage class name, when you see just double quotes mentioned here, that implies that do not use any storage class. Now here I am saying the persistent volume claim that you should be using is EBS CSI PVC, and EBS CSI PVC is here. And then once I've added the volume to the pod, I'm calling that volume, I'm mapping that volume onto a container, and you see here the name is EBS storage, and EBS storage is the name of the volume that I defined here. Hence I'm mounting this volume here. Now let's do a demo for this. So let's go to the terminal. I'll clear my screen, and if I go here, I run kubectl get sc. Sc is storage class. Now if you have been following along with this course, you would also see that your cluster has a storage class. Even if you are Minikube, just run this command, because before I continue with this demo, I want to delete this storage class, and we'll recreate this storage class once we discuss storage classes in a little while. So let's do one thing. I'll take a backup of this storage class first, because we'll have to create it later. I'll run kubectl get storage class. Sc is the short name for storage class. I'll write -o YAML so that it gives me the output of this in YAML format, and then I want to redirect this output onto a file called sc.yaml. I'll press enter, and if I cat this file, then you would see that I have a backup of my storage class. What I'll now do is I'll run kubectl delete sc, and then the name of the sc is standard. It is deleted. If I now run kubectl get sc, I don't see a storage class here. I'll clear my screen now. Let's go to Visual Studio Code and look at the storage classes created here. You can see it, and then let's go to PV here. Here what I am saying is create a persistent volume for me, and the name of the persistent volume will be this. We have seen this exact YAML before, and I've just added a few more sections. Then you see the capacity is 5 GI, access mode is read write once, and then the reclaim policy is to retain. Like in hostPath, usually you would see that it is retain, because if let's say you delete the PVC and you recreate a PVC, you might want to give other pods access to the same data. Similarly, you would also see retain policy when it comes to file storages, because there are multiple pods which were accessing that file storage, and you might not want to delete that file system. Hence you would use retain. With block storage, be it on cloud or be it on premises, I have seen administrators using delete as their reclaim policy. So I have this reclaim policy of retain because this is sort of a file storage that is made available by my host path, since we are not using an actual SAN backend. So what I have done is I have used a host path, and the path is /mount/data. So this is our persistent volume. Then let's see the persistent volume claim. Hold on, why I am not able to? Yeah, what I'll do is I'll right click on this and I'll split this to right, so that we can see both of these. Here we have a PV, and here we are creating a PVC. Now this PVC, again, you see that this is of 2 GI. Even then it will claim this because the PV should be providing storage equal to or more than the PVC. Access mode is read write once, which is same as this, and then there is a storage request of 2 GI. And then we also have a pod, and let me again split this to right so that you can see all all three together. I'll do this. Yeah, here we are creating a pod, and that pod has a volume, and that volume is referencing the PVC that we created here, example PVC, and the name is persistent storage. And if I go to the volume mount, I see the mount path is this, and the name of the volume that it is calling is persistent storage. Now let's go to the terminal and apply these YAMLs. So I will go here, I'll first apply the PV kubectl apply -f pv.yaml, and then I will run kubectl get PV. If I run this command, you see the status is available. So right now this PV is available. There is no claim associated with this. Storage class we have not defined. Reason is blank, and the age is 3 seconds, and the access mode is read write once. Capacity is 5 GI. We can also run describe and see if this provides any further information. Describe, and it is also providing the same information, but it is also providing us the source of this PV. Well, let's do one thing. Now let's also apply the PVC kubectl apply -f pvc.yaml. Now if I run kubectl get PVC example PVC, then I see status is bound. Why is the status bound? Because it would have bound with the PV that we created in the previous step. The capacity is 5 GI, the access mode is read write once, storage class is blank, and then age is 7 seconds. If I again run this command for the PV kubectl get PV, then you would see that previously the status was available, but now the status is bound. And did you notice one thing? In here the PVC we created was of 2 GI, right? But here you see that the capacity is 5 GI. And why this is 5 GI? This is 5 GI because the PV we created was of 5 GI capacity. Now if I do one thing, if I kubectl delete PVC delete -f pvc.yaml, and then also let's delete the PV, and then let's just create the PVC first. Kubectl apply -f pvc.yaml. If I press enter, if I now run kubectl get PVC, you would see that the status is pending and the capacity is not yet defined. If I create kubectl apply -f pv.yaml, and that is applied now. Now if I now check kubectl get PVC's output, it is still pending. Now it is bound since we have created the persistent volume. I'll also run a describe on kubectl describe PVC example PVC, and you can see that failed binding. This was 31 seconds ago. At that point of time the PV didn't exist, but now that it exists, the status should be okay, because if I run kubectl get PVC, I see all things are working as expected. You should always see the status bound. Status bound implies there is a healthy PV associated with this PVC. If I run kubectl get PV, you see that all status is also bound here. So bound is what we want to see. Let's apply the pod YAML. Kubectl apply -f pod.yaml. If I run kubectl describe pod example pod, then if I scroll, if you see the mounts here, I see that this mount is from persistent storage. I hope you are able to connect the dots. You create a PV, then that PV is associated with the PVC, then that PVC is called in the volumes section of your pod, and then you map that volume onto any of the containers where you want to mount it. It is as simple. Just understand the foundational concepts, and be it persistent storage or ephemeral storage, it follows the same thing. So I'll clear my screen now. I will kubectl delete PV example PV. I'll delete my PV. It says the PV is deleted, but is it? My CLI is stuck here. So let me go here into, I'll open Let me open another terminal and I'll zoom in here as well. Now let me run kubectl get pv. It says that the status is terminating. It is not terminated yet. The status is still terminating. Let me run kubectl get pvc. It says that the status of PVC is also bound, so the PV is not yet deleted. So let me run kubectl delete PVC example PVC. It says deleted. So let me open another terminal. So let me write again kubectl get pv, kubectl get pvc, terminating, but none has terminated. If I run kubectl describe pods example pod, then you would see it still has the mount. The point is, if a pod is using a PVC, then you cannot delete that PVC or the PV. So there must be a sequence. So if I go back to my diagrams, you first have to delete the pod if the PVC is being used, then you delete the PVC, after that you delete the PV. It's a protection mechanism by Kubernetes. You cannot delete a PVC if it is being used by a pod. Similarly, you cannot delete a PV if it is being used by a PVC. So if I go here to my terminal, if I run a command now kubectl delete pods example pod, I press enter, now you see everything would have started working. If I go to this tab, it says deleted. If I go to this tab, PVC is also deleted and PV is also deleted. Kubectl get PV, I don't see anything. Kubectl get PVC, I don't see anything. I hope this concept is also clear. Now let's move on to storage classes. See, I had a problem with the previous architecture. Every time someone wanted storage, I was disturbed and I was not liking that. As a Kubernetes administrator, I want my life to be automated. I do not want to go and create PVs all day long, because the storage requests will continue to grow as your cluster and as your applications that run onto that cluster grow. The demand for PV will also increase. So I want a process in place which will ensure that whenever there is a request for storage, whenever someone creates a PVC, a PV must be automatically created. So I, as an administrator, or if let's say your developers are taking care of creating pod manifests and deploying applications onto your Kubernetes cluster, and you are just plain Kubernetes administrator. I'm saying this because now there is, with Kubernetes getting so popular, there are developers who are doing CKAD and they also know how to deploy an application onto Kubernetes. So the infrastructure part, your CK certification resources will be taken care of. People who administrators who take care of administration of the infrastructure and Kubernetes, and then there will be developers who will be deploying their application. So at times we do not want developers to trouble administrators when they want to deploy their applications, and their applications could be using PV and PVCs. So as and when the developer creates a PV, storage is automatically provisioned for them. A corresponding PV is automatically created. That is what is called dynamic provisioning. So if I move a little down, then what is storage class? Storage class in Kubernetes is a way to define different storage configurations, enabling dynamic provisioning of persistent volumes. Persistent volumes is the key here. So if you look at this, you are not defining access mode in the storage class. What happens is, whatever access mode is defined in the PVC, that access mode is set for the PV as well. So what we are doing in this example, we have introduced two storage classes to the cluster. Varun, why we are doing this? If I talk about my Kubernetes cluster, my application could be using file storage, they could be using block storage, and in block storage as well, there could be categories. One could be a storage that provides lower IOPS, one could be block storage that provides higher IOPS. Similarly, there could be a file storage that is limited to a single availability zone when I talk about cloud, and then there could be a file storage storage that spans across different availability zones within a region. So there are different tiers of storage, a gold tier, a platinum tier, and you can do this tiering based on your requirement. Maybe application 1 needs SSD disks and application 2 just requires HDD. Then you have an option to have multiple storage classes associated with your Kubernetes cluster. In the example you see here, we have GP3 type and then we also have IO1. Both of these are coming from the CSI drivers, but their types are different. EBS is the volume type, and within that volume, the type of volume that we are creating, one is GP3 and there is provisioned IOPS, which is IO1. So let's discuss this storage class. Reclaim policy, like we discussed, you would often see delete reclaim policy when we are talking about block storage, and EBS is a block storage solution from Amazon. Type is here in this storage class, type is GP3, and here the type is IO1. IO1 provides you even higher IO. Then we have created a persistent volume claim. This persistent volume claim says that create a PV for me whose access mode is read write once, and the storage I want is 10 GI, and the storage class I want to use is this one, EBS SC GP3, EBS SC GP3. So if I would have provided here EBS SC IO1, then this persistent volume would have used this storage class to create the corresponding persistent volume. Are you getting this point? Very crucial. You can have multiple storage classes, and in your persistent volume claim, you only call the storage class that you want to use. In this example, I wanted to use GP3, hence I called the class which is hosting GP3, and Kubernetes behind the scene creates a persistent volume that matches this PV. The burden of creating persistent volume is now gone, and here you see the corresponding persistent volume. The access mode is that, the reclaim policy is that, the storage class name is again populated from what you gave in the persistent volume claim. Rest of the things are picked up from your storage class. That's the magic that storage class provides. You see that file system is ext4. There could be certain defaults each storage class has to offer. For that, you will have to read the documentation to understand what are the defaults. Then here I have created a pod, and that pod under the volumes section, it is calling EBS CSI PVC, and EBS CSI PVC is what I created here. And then we have named this volume EBS storage. In the volume mounts section of the containers, we see that we are mounting this volume onto this path, and the name of the volume that we are mounting is EBS-storage. As simple as that. This is storage class for you, an important concept which will be always used in production grade implementations of Kubernetes. There is one thing I did not discuss, which is volume binding mode. Wait for first consumer. This says only create the PV once the pod that wants to use that PVC is created. What does that mean? It means that do not allow administrators or developers to just create PVCs. If they have just created PVCs, do not create an associated PV. Why? Because that PVC is not being used right now. Until and unless this pod is created, you do not create this PV. But Varun, what does it do? It saves me costs to begin with. If this pod is not created, then why would I want to provision a 10 GB EBS volume in my cloud provider? My cloud provider will charge me for 10 GB of volume. I don't want that. I only want to provision persistent volumes when there is a pod using that volume. Now, this is one use case why you want to use wait for first consumer. The other option you have is called immediate. So it will provision the persistent volume as soon as PVC is created. But I personally always use wait for first consumer. First is the cost benefit. Second is, let me explain that to you in this slide. What you have here is an AWS cloud. And that AWS cloud, we are using the Mumbai region, and in Mumbai region, we are using 2 availability zones to deploy our Kubernetes cluster. Before I move forward, nodes
and EBS storage are AZ specific. What I mean is, if I create an EC2 instance, that instance will either belong to AZ1 or AZ2. It cannot spread across availability zones. If anyone is new to the concept of availability zone can be thought of as a single or multiple data centers which form an availability zone. In AWS, all regions will have 3 or more availability zones. For example, we are in Mumbai region right now. In that Mumbai region, we are using 2 availability zones. So nodes and storage are AZ specific resources. Now let's say if you created a PVC and a storage was created in AZ1 for you, but when the pod was scheduled in AZ2. How can pod in AZ2 access storage in AZ1? That is not possible. Hence, it is always recommended to use wait for first consumer, because when you do that, the PV is only provisioned once the pod that wants to use that is scheduled. And if the pod is scheduled in AZ2, then automatically the corresponding PV will be created in AZ2, which will make the bound happen immediately. Important concept, a nuanced concept. So let's go to our terminal and do a demo for StorageClass. I'll go to my terminal, and I also want to show you the contents of the file that we just backed up. I'll just close this, expand this, go to sc.yaml. If you see sc.yaml, the important thing to know here is these things. Our provisioner is rancher.io/local path. So this is essentially what is helping us do dynamic provisioning. And I want you to know one more thing. Whenever you are using storage classes in production, it is always that you would be using a CSI plugin for that. So if you see here, I'm using a CSI plugin, and with this CSI plugin, I would pretty much always use a storage class. So let's again go back to Visual Studio Code, and this is our storage class YAML. So let me go to our terminal, and here I will apply this storage class kubectl apply -f sc.yaml. I'll press enter. It says that the storage class is created. If I run kubectl get sc, I see that storage class is created. Now let's do one thing. I'll write kubectl apply -f pvc. I'm using the same PVC like we used in our previous example. I'll press enter. This will just create the PVC. I'll now run kubectl get PVC. It shows me that the PVC is in pending state. Why is it in pending state? Because the corresponding PV is not yet created. Why it is not yet created? Because my volume binding mode is wait for first consumer, and I have not created a pod that would be using this PVC. So if I run kubectl get PV, you see that the PV is not yet created. But as soon as I create a pod that will be using this PVC, I'll see that the PV is created. I'll run kubectl apply -f pvc pod.yaml. I'll press enter. I see the pod is created. If I now run kubectl get PV, voila! A PV was automatically created for you. If I zoom out a little so that this comes in one line, then you see that PV was created, whose name is this PVC-this. Capacity is 2GI. Previously 5GI was used because we were provisioning that manually. If you see that PV, it was of 5GI, but since we are using an efficient process now, our PV will only be created based on the size of the PVC. Our PVC just requested 2GI. Hence, we provisioned a PV that was of 2GI capacity, and you see the status is bound. The storage class we are using is the standard one. Now let me run kubectl get PVC. That status is also bound now. I'll just zoom in a little and I'll run kubectl get pods, and my pod is also running. If I run kubectl describe pods example pod, then I would see that there is a volume that is mounted from persistent storage. I hope all the dots are now connected and you understand what is happening. Now, before I let you go, I want to discuss one more thing. I'll go to my GitHub repository, and if I scroll down, I would want you to read these things. PV and PV binding conditions. I have written the conditions that should be met for a PVC to have a claim on PV, and for that bound message to happen. And then here is a summary chart as well, that the storage class must match. And we also understand these things. If you are mentioning a storage class EBS-SC my storage, then you don't have a storage class with that name. So hence there must be a storage class for with the same name. Only then a PV will be created. And then there are other things that should also match. Access mode should match, and we have seen that. So access mode read write many, then the PV must have read write many. So sufficient capacity must be available. Bounding volume binding mode, we discussed immediate and wait for first consumer. Volume state PV must be available. Matching volume mode, we discussed about file system or block, so they also must match. I think that's all I wanted to discuss. I would request you to go through these GitHub notes because these cover everything that we have discussed.
Why do we need ConfigMap? Forget about what are ConfigMaps. Let's see first, why do we need something like ConfigMap? First is decoupling, and decoupling has been the theme of our Kubernetes course. So if I go to day 11, we started day 11 with a monolithic architecture, which is essentially a single code base deploy onto a single server. Then we upgraded this design into a tiered architecture. In the tiered architecture, we had a web tier, we had an application tier, and a data tier. We also had an optional middleware, which you will pretty much always see if you are dealing with modern application. Here, the single code base was segregated into different tiers so that each tier is only responsible for its respective tasks. For example, web tier was just there to serve the web request. Similarly, application tier was handling the business logic, and the data tier was storing the data, as this is for databases. Then we had middleware. Middleware was doing anything that was not part of the core logic of the application. For example, it was handling authentication, logging, caching, API communication, and service coordination. So what we were doing is we were decoupling the application. How we were decoupling it? We were decoupling it into various chunks. For example, if I wanted to do development in web tier, I would have just touched the code base for web tier. But in this design, if I wanted to change the web tier, then I would have to modify the entire code base to integrate those changes. We were still not satisfied, hence we upgraded this design further into a microservices architecture. If you look at this, we have the microservices architecture. We still had the web tier, the application tier, and the data tier, but what we did was we divided the web tier into different microservices. Similarly, the middleware was divided into multiple microservices. What was the benefit of using microservices? It was that we have decoupled our entire application into different smaller chunks. If any of these microservices failed, for example, then the application will continue to work. Only the part that was handled by that specific microservice will not be available. So if I talk about an e-commerce website, which is the example you see on screen, if wishlist service was down, then users will not be able to access the wishlist, but rest of the functionality of the application will continue to work. They will still be able to browse your product catalog and they will still be able to order. But why are we discussing microservices? So like microservices helped us decouple our entire monolith application into smaller microservices, we want something in Kubernetes which will decouple the configuration files from our container images. Varun, can you expand on that? Let's move to day 12. In day 12, we discussed about Kubernetes services, and I'm taking an example from the same lecture. We have a front-end deployment and we have a back-end deployment. Whenever front-end deployment wants to speak to back-end deployment, front-end deployment pods can use this back-end service, and this back-end service will send the traffic to any of the available pods. But how do my front-end pods know this URL? This URL is known to your front-end pods because you have embedded this into the core logic of the application. But is this the right way to do things? We have been discussing thus far that your application should only be holding the business logic. Rest everything like authentication, authorization, configuration, data, and all these things should be stored somewhere else. These things should be moved out of the core application logic. Hence, we wanted something that would decouple the configuration data. For example, this is a configuration data because this pod will only be able to communicate with backend deployment when this URL is available and this pod knows about this URL. So first is, we know why we need config maps, because we want some way to decouple. Second is portability. Again, let's go to the same example. Let's say this is my production cluster and this was my backend service for production. Now, if I want to, let's say, deploy this application onto my development environment, I will have to change my application code to reflect the name of the service that is there in my development environment, because here I am calling it backend service, but ideally if this is production, I should have called it backend-prod, for example. And then whenever I want to deploy this service onto my development cluster, I would call this backend-svc. So in that scenario, if I move this application onto my development cluster, I will have to change the code base of my application to the development cluster. I would have to tell my application that when you want to reach backend deployment, you should be reaching out to backend-dev. And that again, how many times will I have to update my image? Because you not only have development and prod environment, you have staging, you have QA, and so on. So this is complex. So we needed something that could help with first decoupling, second with portability. Third is inject config data into pods. Whatever configuration I have that my application requires, I should be able to inject that configuration onto my pods so that my application can use that. To fix all these things, Kubernetes architects decided we want something that can be used to inject configuration data into pods, and hence ConfigMaps were born. So let's go to day 12. Now let's say if this configuration is offloaded to a config map, then I don't have to code it anymore in my application code. I will just tell my application code that when you want to reach backend deployment, just refer that configuration file, and that configuration file will know how to reach backend deployment. Essentially, that file will have that URL that application can consume. Now, even if we move to dev environment, the logic will still the same. The application will know that I have to reach that file or that config map when I want to reach the backend service in the development environment, and it will do the same. So we have achieved both decoupling and portability. So let's now see what is config map. Used to store non-confidential key value configuration data. This we already understand. Config maps do not provide encryption or secrecy. So when you create a config map object, everything is in plain plain text. If you want some sort of secrecy, if you are storing sensitive data, then you would be using secrets, which we'll discuss after ConfigMaps. Pods can consume ConfigMaps in three primary ways. First is they can consume them as environment variables, as command line arguments, which is less common, and the last one is as configuration files via mounted volumes. So we'll be seeing a demo of both of these, as environment variables and as configuration files. So I hope we have a good understanding of what are config maps and why do we need them. So let's move to Visual Studio Code and create our first config map. So before I discuss how to create config map, I first want to show you how do you inject environment variables into a pod. What are environment variables? Environment variables are key value pairs, and your application can refer to that key when your application wants to know the value for it. So what we'll do is we'll first see environment variables so that you have a good understanding of what environment variables are to begin with. We have a simple YAML, and if you look at this, we have been using this YAML since the beginning. I'm calling it front-end deploy. I'm only creating one replica. This deployment will be handling any pods that have app is equal to front-end label, and that is the label that I have assigned to it. We are using an Nginx image. Only this is the part that is new, and we also saw this briefly in our downwardAPI demo. Let's see what is happening here. What we are saying is env is used to define the environment variables, and like you see, it is right underneath the first container, which implies all the containers. You can have multiple containers in your pod, and each of those containers can define their own environment variables. So we are defining two environment variables here. If you see, env is a list, so you can have multiple environment variables here. I only have two. The name of my environment variable is app. So once I apply this YAML and I go into the container, the key of the first environment variable, so let me show this to you. So app is front end. This means is this is a key and this is a value. The key for my environment variable is app and the value for my key is front end. Here the name is app and the value is front end. The second environment variable is called environment and the value for it is production. Let's apply this YAML now. I'll go to my terminal. I'm already in day 28. I will zoom in a little and then I will run kubectl. Let me first clear my screen. kubectl apply -f and I'm calling this ev.yaml. So I'll write ev, press tab, hit enter, and it says that the front end deployment is created. Now let's do one thing. I will run kubectl exec -it and the name of this pod is front end deploy and some random text. Then I will use double hyphens and I want to run the command print env. This will just print the environment variables, and you see here I have two environment variables like I defined in my YAML. App is equal to front end and environment is equal to production. So if I go into this pod, if I exec into this bin bash, if my application wants to access this environment variable, it can just refer to it with whatever means that application supports. For example, if I am using shell scripts, then I can simply access the variables by adding a $sign. So $sign app, if I write here, this should spit out front end. So different applications or different programming languages have different ways to access environment variables. In shell scripts, it is $sign and the key of the environment variable. I want you to understand is there is no need to keep this uppercase, but it is widely accepted in this industry that whenever you want to define a key for an environment variable, it is better if you use uppercase for that, which is why we are using uppercase. So I hope this is understood. I'll now exit from the container and then let's do one thing. What I'll now do is I'll run kubectl get pods. And when I run this command, you see that this pod has been running for last 2 minutes and 7 seconds. So let's go to our Visual Studio Code and I will change this from front end to back end. I'll save this and then I will again apply this YAML, kubectl apply -f ev.yaml. It says that it has applied and it has configured. Now let's do one thing. I will run the same command again, kubectl exec. I didn't have to add a -it here. If I didn't want an interactive terminal, I added it just because I have the habit of typing it. So if you are just running plain commands, then you don't have to add -it. So I'll name the pod. The name of the pod is this, and then I will write print env. You see that it has also updated. But there is one thing that I want you to note. If I run kubectl get pods, you see that the age of the pod is 49 seconds, which implies that the previous pod was deleted and this is a newly created pod. So if you change the environment variable in your manifest and apply it, then Kubernetes will take a rolling restart for all the pods in your deployment. Since our deployment only had one pod, it was restarted. Now let's move on to the ConfigMap section. What I'll do is I'll delete this kubectl delete -f ev.yaml. So this will delete anything that is available in ev.yaml manifest. I'll clear my screen. Now let's go to the meteor section, which is ConfigMap. So let's go to Visual Studio Code. I'll open cm-1.yaml, which holds my config map. API version is v1, and let's go to the terminal and run our favorite command, kubectl API resources. So this will tell me where do config maps belong. If I scroll above, here you see ConfigMaps is the name, the short name is CM. So kubectl get CM will get you all the config maps in your namespace, and config maps are namespaced. So if you have an application 1 namespace, then pods in application 1 namespace can only access the config maps that are created in app1 namespace. The kind is config map. Now let's go back to Visual Studio Code, and here the kind is config map. Under the metadata section, I have specified the name of the config map, which is frontend -cm. Then data is something that you will always see in config maps, and then I am saying app is equal to frontend and environment is equal to production. And we know everything in YAML is key value pairs. For example, data is the key and the value is this. App is a key and value for that app is front end. This is an important concept to grab, and I'll look back into it in a few moments. Now let's open the deployment YAML, which will be using this config map. Understand that before this, we were defining the environment variables directly in the pod manifest. So we had app and the value was front end in our example. So we defined that manually here. However, when it comes to config maps allow you to inject environment variables into your pods, and we'll see how does that work. So let's go to CM1. Here we have defined this. Now let's open front end CM1. What I'll do is I'll right click here and I'll split this to right, and I'll close this so that we can see both the YAMLs side by side, not ev.yaml. I wanted CM1. Let me again split this to right. Yeah, I will close this. Now we have CM1 on the left and our deployment YAML on the right. So let's see what is going on here. Till here, we already understand it's the same manifest. But here what we are doing, we are saying environment, name is app. So this is app, what you will see inside the container, the key. And then we are saying that take the value for this app from a config map, and the name of that config map is front end CM, this. And we are saying in that config map for the value of app, you should look at key app. So here we are saying look at key app. So app is front end. This could be a little confusing. Why are these same? So let me just quickly clarify one thing for you. This could be app name, and here could also be app name. Understand that whenever you are in the container, the key of the environment variable will be app that you define in this name here. And then here what we are saying, this config map could have multiple environment variables, but what we are saying is for the value of app, you look at the key app name, and the app name key is this. Remember what I said in YAML, everything is key value pairs. So here I am saying the key that you must refer to get the value for this app is app underscore name, and app underscore name's value is front end. So this essentially will fill app is equal to front end. And then for the second environment variable, we are saying the same thing. For environment, you should refer the key environment. You should keep these same for simplicity, but I just changed it so that you could understand this in a better way. So let me just remove this. I'll save this, and then in this I'm also creating a service which is a node port service, which the node port for that is 31,000. If you have been following along with me throughout this course, you know that we have set up kind cluster. We configured our kind cluster in day 8. If I quickly show that to you, in day 8 we configured kind cluster, and then in day 12 we improvised our design of kind cluster so that we can use the node port service. So if you are using kind, then your node port should be 31,000, and with kind we can access our node port using localhost. So if you have some other deployment of node port, you could be using your worker nodes IP to access the node port. Although we don't need this node port service in this particular demo, but in the next one we'll need that. So let's go to our terminal again. I will apply both the YAMLs. I'll apply kubectl apply -fcm1.yaml, and then I will apply kubectl apply -f it is frontend cm1.yaml. Did you notice one thing? I applied the ConfigMap YAML first, and why did I do that? Because if you look at my YAML, my front end cm1, which is my front end deployment, is referring to a config map. The config map must exist so that these values can be integrated. So let's go back to the terminal again. So the sequence is important. You first apply the config map and then the deployment YAML. So I'll press enter, and if I run the same command again, kubectl exec, and the name of the pod is frontend deploy this, and then I will run print env, and like we saw before, app is equal to front end and environment is equal to production. We defined environment variables. The benefit that we received is there could be several environment variables, and it is not wise to enter all those environment variables in this YAML. Like we saw in our previous demo, it is recommended to use config maps for the same so that you can decouple it from your pod manifests. So let's close this, and then now let's do one thing. Let me change the value for a particular field. Understand that previously we were directly changing the pod manifests, but if we now want to change the value, we'll just be modifying the config map. Let's go here from front end. I will just change this to backend. Now let's go to the terminal. I will kubectl apply -f. It was cm1. I'll apply this. It says that the config map is configured. If I now run kubectl get pods, the age of my pod is still 2 minutes. So what we learned here? We learned here that when we were defining environment variables like this statically, everything inside the pod manifest, and we updated that and reapplied the manifest, we saw that the pod was automatically restarted, and that was something which is not controlled, and that's not right. That's not predictable. We want things to be predictable. with ConfigMap, when you applied this ConfigMap, the pod was not restarted automatically. Now you have applied the changes, but Varun, how do I see my changes? Because if I run the same command again, print env, I see that my app is still front end. I want this to be backend. For that, we'll have to take a rolling restart for our deployment. So if I run kubectl, I think rollout, then restart, and then name of the deployment, yeah, deployment, and the name of the deployment is frontend-deploy, and then I'll press enter. So this will restart my pod. If I now run kubectl get pods, I see that it is running and the age is 7 seconds. So if I now run kubectl exec frontend print env, then I see my app is equal to backend. The value for my environment variable is now updated. So now we have understood how to use ConfigMap, how to inject ConfigMaps as environment variables. In the next demo, what we'll see is how to inject ConfigMaps as volumes, and this is used when you want to inject your configuration files into your pods. So let's go back to the terminal and let's delete whatever we created in the previous demo. kubectl delete -f cm1.yaml, and then kubectl delete -f frontend cm1.yaml. All things are deleted. I'll clear my screen now. So let's see what is happening in our demo2's YAMLs. Let's open cm2. Again, we know these things, and till here it is the same YAML. Now what we are doing here is we are saying the key is index.html and the value for that key is this, but we are using a pipe symbol here. Why do we use a pipe symbol? Pipe symbol is usually used when you want to preserve the formatting. So when you talk about HTML, YAML, you want those things to be in a specific format. So this is HTML. I want, when this data is there in my container, I want this data to be in the same format. Hence we use the pipe symbol. So what is there in this file? This is a normal HTML file which is saying the title is welcome, and it says this page is served by Nginx. Welcome to Cloud with Varjosh. And if I move to frontend cm2.yaml, which will be consuming this config map, I'll open this, and let me also open cm.book here, and I'll split this to right. I will close this here. Let me just give you some more real estate, and let's go here, and here in the view section I want this to be word wrapped, and here let's add a hyphen so that these lines go away. These lines are there because I'm not given resource requests and limits. Okay, till here we know what is happening. We are using the same thing. It is app is equal to front end, environment is equal to production, and then we are calling the app key and calling the environment key like we saw in our previous demo. What is new? New is this volume. We are mounting the config map as a volume. What we are saying is volumes, name of the volume is HTML volume, and we have been seeing before that then you write the type of the volume. When we were using hostPath, we were writing hostPath here. When we were discussing emptyDir, we were writing emptyDir here. Since we are dealing with config map, we will write config map here. Extremely simple. You first add a volume to your pod, and once that volume is added, one or more containers in your pod can access that volume using volume mounts. So here we are saying the volume is of type config map. And what is the name of the config map that we want to use? We want to use the front end CM. So that is what we are referring here. Then we are saying here volume mounts, name is HTML volume, mount path is this. Now what is this path? This is the default HTML path in Nginx, and inside this you usually have an index.html file which serves your static content. Then for now let's keep it till HTML only, and we'll see why we are doing this. And then we are saying this mount path is read only. So whatever we will be mounting will be only read only. There is an important thing I want you to understand. Config maps are mounted as directories in Kubernetes. So if you try to mount a config map at a path that is a file, for example, if I had index.html here and you still tried to map this config map onto here, mount this config map here, then it would have failed, because Kubernetes does not allow you to map a directory onto a file. So since config maps are treated as directories, we can only mount them onto a directory. There is a catch. That catch we'll see in a little while. So for now, this looks good to us. And then here we are creating a similar node port service, and we'll be using this node port service this time. So if I close this, and then let's go to the terminal and apply this config map. kubectl apply -f cm2.yaml. And previously we created the config map, but I didn't show you the describe command or the get command. So let's run kubectl get cm. If I run this, you see there is a front end CM, and this is there, which was created by default 38 days back. Front end CM is here, and in the data block it says 3. So let's do a describe kubectl describe cm front end CM. If you see here, whatever we wrote in the YAML is available here. So under the data section, you have the key app whose value is front end, then you have a key environment whose value is production, and then you have the key index whose value is this. So let's now also implement the deployment YAML. So kubectl apply -f front end cm2.yaml. I'll press enter, and now if I run kubectl get pods, I see that this pod is running. So if I go to my browser, see I have the GitHub notes opened. I sincerely urge you to GitHub notes whenever you watch the videos. After that, refer the GitHub notes, because this has detailed information. There are many things that I want to explain, and at times because of time constraints and because of XYZ complexities, I cannot cover everything that is available. But in the GitHub notes, I still add a few things that I feel are important and you should know. So after the videos, do refer the GitHub notes. I'll go here, I'll access localhost :31,000, which is my port. I press enter, and I see this page is served by Nginx. Welcome to Cloud with Varjosh. So what did we do here? We essentially outsourced something to ConfigMap. There was a configuration that was to be added in my earlier container image. We didn't modify the container image, we just added a config map, and my application is now using that config map to display a custom page of Nginx to you. Welcome was the title that you see here, and then this is what we added. So let's now do one thing. I will run kubectl exec. The name of the pod is this, and then I will run print env, and you see app is equal to front end and environment is equal to production. So let's go to the config map again, and let me do one thing. Let me again change this to backend, and then here also I will add one more line. I'll copy this, I'll paste it. This will be 2, this is also 2, and then I will write here the dark side of the moon. I'll add few exclamatory marks for effect, and then I will save this. So let's go back to our terminal, and what I will do is I'll just apply this config map, kubectl apply, and before I apply this, I also want to exec into this pod and show what all contents are there. I forgot to do that, I'm so sorry. I'll write sh bin, let's use bash, that is born again shell, and then I'll also add a -it because I want an integrated terminal. I'll press enter. I'm inside the pod. I'll clear my screen so that you have real estate. Then I will run cd user share nginx html, and then let's press enter. If I run ls, you see 3 files here: app, environment, and index.html. So what we learned here, all the keys under the data, so we had 3 keys: app, environment, and index.html. These are copied as files onto your container. Important concept to grab: everything that is inside data will be copied onto the specified path. The path that we specified was this, and we said map the entire config map. An entire config map had 3 keys, and we'll see in a little while how can I only map what is needed, because in our scenario we only wanted index.html, correct? And all the files that were created will have the values as defined here. So index we have already seen. If I cat into app, you see it has front end in it, and if I cat on environment, only if I could spell right, then you would see production here. Yeah, and if I cat index, you will see these contents here. So let me now exit this, and if I go to Visual Studio Code, I see that this is here, CM2 is here, and we have modified a few things. We have changed the app to backend, and we have also added the dark side of the moon in my index.html. So let's go to our terminal, and I will run kubectl apply -f cm2.yaml. I'll press enter, and it says configured. Let me run print env first. App is front end and environment is production. So the changes that we performed here are not reflected, right? Let's go inside the pod. I'll again cd into the same path, user share nginx html, enter. I will run ls here, and I'll run cat app. What? It has backend. Why is this? If I cat on index.html, I see the dark side of the moon here. Why did this happen? When you mount ConfigMap as volumes, the changes are dynamic. So if I change anything in here, and all these things are mounted as volumes, if I change anything here, and as you see, I am adding the entire config map as a volume, entire config map. So here I was just calling the environment variables from here. So this part remained the same, but any part of the config map that is mounted as volumes is changed dynamically. And we saw that app is equal to backend is reflected in the pod. You see, app is equal to backend has changed, and also the file that we modified, that content is here. So if I go to my Chrome browser now and I hit refresh, you see the dark side of the moon. The changes to the config maps when you mount them as volumes are dynamic, and most of our applications require dynamic. So if your requirement is similar, then you can use these. Now I want to show you one more thing. Right now, whatever we did, all our content of config map was mounted, but I don't want that. I only want to mount index.html, nothing else. So what I'll do is I'll go here, I'll add items here, and inside item I will add the key that I want you to use is index.html, and the path that I want you to use is index.html. So what am I saying here? I'm saying that I only want you to use this file that is called index.html. So index.html and path, and I want you to name that file index.html inside this directory. So let's go to the terminal and give this deployment a rolling restart. I'll exit this. I'll run kubectl rollout restart deployment, and I only have one deployment. I'll press enter, and it says it is restarted. If I now, let's say, exec into this pod, kubectl exec front end deploy, I'll run bin bash. I'll also add -it here, and then I will run cd user share nginx html, and then I'll run ls here. Oh, I didn't apply the manifest. I'm so sorry. Please pardon me. I'll have to apply the manifest as well. kubectl apply -f frontend cm2.yaml. So it says configured hyphen. I'll run kubectl get pods because whenever you make changes in the volumes, I've made changes in the volume part, hence the pod is restarted automatically. So if I run kubectl exec -it, or let's do one thing, let's not run -it. I will run ls user share nginx html, and you see if I run ls on this path, I now only see index.html because I have mapped this entire config map as volume, but I have specified that only map this key. This key is index.html, and index.html is here. So before I let you go, I want to explain one more thing. So I said that config maps are mounted as directories in Kubernetes. What if you do want to mount the config map as a single file? How do you do that? So for that, you have something called subpath. If the config maps are mounted as directories, then you have to supply the directory here. You cannot have a file here. For example, I cannot have index.html here and then apply this YAML. It will create the pod, but your pod will not be in running state. It will be in some sort of error state. If you want this sort of setup, then what you can use is you can use here something called subpath. So it is subpath, and then in the subpath you can mention index.html. And I can also remove this from here, because in subpath you only add specific keys. So here I'm saying subpath, the file, the key that you should map is only index.html, and the path where you should be mounting this is index.html. So I'm referring a file here. Now this file will be replaced by this index.html. So let's do one thing. Let's quickly apply this. kubectl apply -f frontend cm2.yaml. I'll press enter and it says that this is configured, and if I do ls, I will see that config map there. So let me do one thing. I will exec into this, and let's do one thing. Let's cat the content user share nginx html index.html. If I press enter, you see that we have this information here. But let's do one more thing. I'll go here and I'll add one more line. I'll just add a dark side of the moon too, and then I go here and I will apply this YAML file again, and this is the cm2.yaml, and then I will again exec into that pod. Now what I want you to see is when you are using subpath, the changes that you are doing in the config map are not dynamically updated. When we were using without subpath, when Kubernetes was mounting config map as directories, then it were whatever changes you did in the config map were automatically reflected inside the container, but with subpath changes are not reflected. So if I go here and I cat again, you see I still have this. Now I have completed all the demos that I wanted for config maps, and all these demos will help you be extremely confident when you are dealing with production grade applications, because all of them will be using config map. Let's now go to our diagrams and continue with our next section, which is why do we need secrets. Before I start this section, I have a request. If my content is helping you in any way, any small way, then please like my videos, subscribe to my channel, and if it is possible for you, then please do leave a comment, even if it is just a hi or a thank you note. It helps me more than you know. So yeah, let's continue with secrets. Applications often require access to sensitive data such as database credentials. When you want to access a database for your application, you will have to provide database credentials. API tokens if your containers are accessing any third-party services or applications, then you would be using something called API tokens for authentication. Then SSH private keys. If your container is connecting to a server over SSH, then you will have to provide private keys. TLS certificate will provide you with identity verification when you are accessing something on HTTPS. These are the use cases where our containers were holding sensitive information, and we learned in our previous section with ConfigMaps that everything that you define in ConfigMap is in plain text. So we want some sort of encoding or maybe encryption that will hide the sensitive data. So what is a secret? Stores and manages sensitive information. Secrets are base 64 encoded. Now this is an important point here. There is a difference between encoding and encryption. So for example, if you encode something using base 64, then you can decode it online, or you have utilities in your Linux which can be used to decode that. And when we talk about encryption, anything that is encrypted can only be decrypted by a specific key. And if that key is not available, then you cannot decrypt it. In essence, encoding is useful, but it is not as secure as encryption. So there are ways via which you can further secure your secrets. So whatever we will discuss in this lecture, we'll talk about encoding, not encryption. But I would encourage you to look at external secrets managers like HashiCorp Vault, AWS Secrets Manager, or sealed secrets, which can be further used to secure your secrets. In the default secret object that is available at our disposal in Kubernetes is encoded using base 64, and then you can limit the access to those secrets using RBAC, which we'll discuss in our security section. Then similar to ConfigMap, pods can consume secrets in three primary ways: as environment variables, as command line arguments, which is less common, or as configuration files via mounted volumes. Let's do a demo on this. So I'll go to Visual Studio Code. I will close both of these YAMLs. I will open secrets1.yaml. The same syntax as ConfigMap, you just have a type which is opaque. Opaque is used for any arbitrary key value data. So inside the data we have a DB user whose username is this, and then we have a password, and this is the password. So this is base 64 encoded right now. How do I decode it? So I'll copy this, I'll go to my terminal, I'll clear my screen, I will write echo -n, I will paste that, and then I will write base 64 -- decode. I'll press enter, and it says the decoded text is front end user. So for example, if I had to create an encoded version of front end user, then I would copy this, and then I will add echo -n, then I'll add this, and then I'll write base 64 here and press enter, and it gave me the same like we saw here. So it is as simple as that. This is my DB user, and this is the password for my DB. It is exactly similar to how you would use ConfigMap. It's just ConfigMap is used for configuration files and secrets are used for sensitive information. For example, you would use environment variables like you have defined here for defining, your regular key value pairs. But when you are using some configuration files that, for example, if you are using private keys, if you are using certificates, then you would usually have something like mycert, and then you can, this, and then pipe it, and then you can have your certificate here. So that is the use case that you would be seeing in your production environments, and when we'll see this in a while. Right now, so we have this. Let's see the corresponding deployment YAML. I'll open this to the right, I'll close this, and then it's similar. Name is DB user. Value from, we are saying that take the value from a secret key reference whose name is frontend -secret, and this is the name frontend secret, and then the key is db user. So the name db user environment variable key inside your container will have a value of this, and similarly the db password is the second environment variable whose value will be db underscore password, which is this. So let's go to our terminal and apply this. And before I do this, I think I have my previous pods running. Okay, it is single pod is running, so I'll run kubectl delete -f cm2.yaml, and I'll also delete my deployments. Kubectl delete -f, it was frontend cm2.yaml. This is also deleted. I'll clear my screen. Kubectl apply -f secret -1.yaml. I'll press enter. Kubectl get secrets will show me the secret. Type is opaque, data is 2, and age is 5 seconds. Then I will run kubectl describe secrets frontend secret, and you see here db password, and this information is hidden from you. And if I run a kubectl get secrets frontend secrets -o yaml, I can see that what were the encoded username and password that I entered in my YAML. So I want you to understand that whatever data you put here should be base 64 encoded. Okay, and then we'll go here, and now I will apply the kubectl apply -f frontend secret 1.yaml. I'll apply this, and if I now run kubectl exec front end this, and then I will print the environment variables. If I do that, you see here front end user, and there is front end pass. I want you to note one important thing. The Kubernetes object that had the information, these values were base 64 encoded, but when Kubernetes injected this into your container, they were not base 64 encoded. It copied them, it created the environment variables in decoded format. Your application does not have to burden itself in decoding these username or password. It will just have to consume it like it will consume any other environment variables. How? In your application, you would configure the db username is this, and the db password is db_password, and it will access the environment variables to access it. So here we have decoupled the db connection. So let's go back to our Visual Studio Code, and then we'll see a second example. I'll close this, and then in the second example we are just mounting secrets as volumes. So I'll split this to right, I'll close this, and if you see here, we have a volumes section which is at the top. We are saying that the volume that you should be using is secret volume. That is the name that we are defining, and we are saying this volume is of secret type. So like we saw before, in ConfigMap you have ConfigMap here, in emptyDir you have emptyDir here, in hostPath you had hostPath here. So since we are using secrets right now, we have secret here, and the name of the secret that you should be using is frontend-secret, which is this one. And then we are calling this volume in the volume mounts section. We are saying the name of the volume that you should be using is secret-volume, which is this one, and then the secret directory should be mounted in etc/secrets path. So all these contents, so for example db_user and db_password, these keys will be available as files inside this path, and when you access these keys or these files under this path, you would see these values here, not exactly these values because the values will be decoded. So let's now apply these YAML. So first let's delete the previous deployment, kubectl delete -f frontend secret 1, and then let's apply the new YAML, kubectl apply -f frontend secret 2.yaml. And then if I now run kubectl get pods, I see that pod is running. I want to exec into the pod now. So let's go inside the pod, kubectl exec, I'll add -it for integrated terminal, and then I will write front end, and here I will write bin bash. And if I go to cd etc secrets, and why cd etc secret, because that is the mount path where we have mounted these. So if I go here, if I run ls, you see both of these files are created. So all the keys are copied as files inside this directory. So I'll go here, I will run cat db underscore user, and you see this is here in the decoded format. Similarly, I can do it for password as well, and you see that is also in decoded format. I hope this is understood. Rest of the things are similar to ConfigMap. Rest of the concepts that we learned in ConfigMaps will still apply to secrets. It is just that you are using secrets for sensitive information. I think that's all I wanted to discuss.
Thanks for watching this storage masterclass. If you found it helpful, make sure to like, subscribe, and check out the full CK 2025 playlist for the complete series. We are covering everything you need to crack the exam and understand Kubernetes the right way through real world examples and practical use cases. You will find links to all the individual lessons and GitHub notes in the description. Got questions or feedback? Drop a comment below or connect with me on LinkedIn or GitHub. I always love hearing from fellow learners. Until next time, keep learning, keep building, and I'll see you in the next one. Thank you very much.